Hello there and welcome back to the Science Sleepy Minds. Tonight you're standing at the very edge of everything. Not the edge of your bed, not the edge of your patience with that neighbour who mows the lawn at 7 in the morning, but the actual edge of the observable universe. Picture it. 46 billion light years in every direction. A bubble of space and time so incomprehensibly vast that your brain quietly folds its arms and refuses to participate. And somewhere out there, scattered across this canvas of galaxies and nebulae and cold drifting dust, there are objects so dense, so gravitationally greedy, that not even light, the fastest thing in existence, can escape them. Black holes. You're about to visit every single type, and you probably will not survive any of them, but hey, that is what imagination is for. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're at it, drop a comment telling me where you're listening from tonight and what time it is where you are. I always love reading those. Someone is always tuning in from a place I've never heard of, and that is half the fun. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You take a breath. The stars around you are not twinkling the way they do from your backyard. Out here, above the atmosphere, above the thin blue veil that makes starlight shimmer, every point of light is a steady, unwavering pin. Thousands of them. Millions if you let your eyes adjust. And each one is a sun, burning through its nuclear fuel, fusing hydrogen into helium, helium into carbon, carbon into oxygen, climbing that elemental ladder rung by rung. Most of them will live quiet lives. They will burn, they will swell, they will shed their outer layers in a gentle cosmic exhalation and leave behind a dense little ember called a white dwarf. Respectable, dignified. The universe's version of retiring to a cottage by the sea. But some of them, some of them, are not going to go quietly. The massive ones, the stars that outweigh our sun by 10, 20, 50 times, they burn through their fuel with reckless, almost teenage urgency. They are the rock stars of the cosmos, living fast and dying spectacularly. And when they die, when that final moment of collapse arrives, they do not leave behind a gentle ember. They leave behind something far stranger, something that warps the fabric of space and time itself into a funnel from which nothing returns. You're going to fall into that funnel tonight. Multiple times, actually. Different shapes, different sizes, different flavors of existential dread. But we're going to do it slowly, gently, the way you might wade into a warm lake on a summer evening. No rush, no panic. Just curiosity and a soft voice guiding you through the dark. The idea of a black hole is not as modern as you might think. Most people assume it is a 20th century concept, born from Einstein's equations and the feverish scribbling of theoretical physicists. And yes, general relativity certainly gave us the mathematical framework. But the seed of the idea was planted much earlier. In 1783, an English clergyman and natural philosopher named John Michell, a man whose name is criminally underappreciated in the history of science, wrote a paper for the Philosophical Transactions of the Royal Society, in which he imagined what he called dark stars. His reasoning was elegant. If you throw a ball upward, gravity pulls it back. Throw it faster, it goes higher. Throw it fast enough, it escapes entirely. That speed is the escape velocity. Michel simply asked, what if a star were so massive and so dense that its escape velocity exceeded the speed of light? Light itself would be trapped. The star would be invisible, dark, a dark star. Now Michel got some of the physics wrong. He was working with Newtonian gravity, not general relativity. And he imagined light as tiny particles affected by gravity in the same way a cannonball would be. Scientists still argue whether Michel should be credited as the true conceptual father of black holes, or whether that honour belongs to Pierre-Simon Laplace, who independently reached a similar conclusion a few years later. It is one of those delightful historical tangles where two brilliant minds arrived at the same wild idea from different armchairs. But the important thing is this: over 200 years before anyone had the technology to detect a black hole, someone sat in a study in Yorkshire and thought, what if there are invisible stars? That is the kind of audacity that makes science wonderful. You let Michel's ghost fade back into the 18th century and turn your gaze forward. The star field around you is shifting now, subtly. You're drifting, carried on a current of narrative convenience toward a region of space where the stars are slightly more crowded, where the glow of a nearby nebula paints everything in hues of rose and violet. Somewhere ahead, hidden in that glow, your first black hole is waiting. Not the biggest, not the strangest, but the most common type in the universe, born from the dramatic death of a massive star. And to understand it, you are going to need to watch that death unfold from the beginning. There is a strange comfort in knowing that destruction on this scale follows rules. It is not random, it is not chaotic, it is physics, elegant and merciless, playing out the same way it has played out billions of times across billions of years. The star you're approaching does not know it is doomed. It is just doing what stars do, burning, shining, converting mass into energy, with the quiet diligence of a factory that has never missed a shift. But deep in its core, the clock is ticking, and when it stops, you're going to want to be watching. So settle in. Pull the blanket a little higher. Let your breathing slow and your thoughts soften around the edges. The first black hole is close now, and the story of how it was made is one of the most violent, beautiful things the universe has ever choreographed. The thing about gravity is that it never stops whispering. It is the quietest of the four fundamental forces, the weakest by an almost embarrassing margin, and yet it is the one that shapes everything. Electromagnetism is flashier. The strong nuclear force is, well, stronger. The weak nuclear force handles its own peculiar business inside atomic nuclei. But gravity is patient. Gravity plays the long game. It is the force that gathers clouds of hydrogen into stars, pulls stars into galaxies, and bends the trajectory of light across billions of light years. And when it wins completely, when it overwhelms every other force that might resist it, you get a black hole. You're floating now in a quiet stretch of interstellar space, and you decide to build one in your mind from the ground up. Start simple. Imagine throwing a tennis ball straight up into the air. It rises, slows, stops, and falls back down. Gravity wins. Now throw it harder. It goes higher before returning. Throw it at about 11 kilometers per second, roughly 25,000 miles per hour, and it will leave Earth entirely, sailing off into space without ever coming back. That speed is Earth's escape velocity. Every object with mass has one. The Moon's is lower, about 2.5 kilometers per second, because the Moon is smaller and less massive. The Sun's escape velocity from its surface is much higher, around 618 kilometers per second, still manageable for light, which travels at roughly 300,000 kilometers per second. Light leaves the Sun without breaking a sweat. It does not even glance back. But now imagine compressing the Sun, not changing its mass, just squeezing it smaller and smaller. As the radius shrinks, the surface gravity increases and the escape velocity climbs. Squeeze the Sun down to a sphere about 6 kilometers across, roughly the size of a modest city, and the escape velocity at its surface reaches the speed of light. At that point, light can no longer escape. Nothing can. You have created a black hole. The boundary where the escape velocity equals the speed of light is called the event horizon, and it is not a physical surface. You would not bump into it. There is no wall, no membrane, no dramatic gate with a sign reading "Abandon all hope." It is simply a mathematical boundary, a point of no return drawn in the geometry of space-time itself. Cross it, and every possible path forward, every direction you could travel, including backward, leads deeper in. Even if you fired your engines at full thrust pointed directly away from the centre, you would still fall inward, because inside the event horizon, all paths through space-time curve toward the singularity. It is not that you lack the speed to escape, it is that the concept of a way no longer exists. This is what makes black holes so fundamentally alien. They do not just trap things with brute force the way a spider's web traps a fly. They reshape the very stage on which physics performs. Space and time, those two things you have relied on your entire life without giving them much thought, become warped and twisted in ways that defy everyday intuition. Near a black hole, time slows down relative to a distant observer. A clock hovering just outside the event horizon would tick so slowly that someone watching from far away would see it nearly frozen. Meanwhile, the person holding the clock would feel time passing normally. They would check their watch, shrug, and wonder why everyone else seemed to be moving and fast forward. This is not science fiction. It is a direct prediction of Einstein's general theory of relativity, published in 1915, and it has been confirmed by experiments ranging from precise atomic clocks on airplanes to the GPS satellites orbiting Earth right now. Your phone's navigation works correctly only because engineers accounted for the time dilation caused by Earth's comparatively gentle gravity. Black holes just take that same effect and crank it up to an absurd degree. At the very centre of a black hole, or at least at the centre of the mathematical model, lies the singularity. This is where all the mass that formed the black hole is theoretically compressed into a point of zero volume and infinite density. If that sounds nonsensical, congratulations, you're paying attention. Physicists broadly agree that the singularity is a sign that general relativity, magnificent as it is, breaks down under these extreme conditions. It is the theory throwing up its hands and saying, "I cannot describe what happens here." To truly understand the singularity, we would need a theory of quantum gravity, a framework that merges general relativity with quantum mechanics, and despite decades of brilliant effort from thousands of physicists, that theory remains elusive. String theory offers some possibilities, loop quantum gravity offers others. Scientists still argue whether the singularity is a real physical feature of the universe, or merely an artifact of incomplete mathematics. It is one of the deepest open questions in all of physics, and the fact that it hides behind an event horizon, forever shielded from direct observation, makes it all the more maddening. Here is a quirky little detail that most people never consider. The term black hole itself is surprisingly recent. For decades, these objects were referred to by clunky names like gravitationally completely collapsed objects, which sounds less like a cosmic phenomenon and more like a bureaucratic filing category. The snappy term black hole was popularized by physicist John Archibald Wheeler in 1967 during a lecture, though there is some debate about whether he truly coined it or simply amplified a phrase already circulating among scientists. Wheeler himself claimed a member of the audience shouted it out, and he liked it so much he adopted it. Regardless of who said it first, the name stuck instantly because it is perfect. Two small words that capture the essence of something vast and terrifying and irresistible. You let that thought settle as the stars around you continue their slow, silent rotation. Gravity has whispered its secrets to you, and now you understand the blueprint. A black hole is what happens when gravity has the final word. No negotiation, no appeal, just collapse, curvature, and a boundary beyond which the universe keeps its darkest secrets locked away. And now that you know how the lock works, it is time to watch one being forged in the most spectacular explosion the cosmos has to offer. The star you're approaching is a monster. Not in the horror movie sense, though. Give it a few million years and it will deliver something far more terrifying than anything Hollywood has ever dreamed up. No, this star is a monster in the purely physical sense. It is roughly 25 times the mass of our Sun, a blue supergiant burning with a surface temperature that would make a welding arc look like a birthday candle. Its light is not the warm yellow gold of our home star. It is a fierce, electric blue-white, the kind of light that does not invite you to sit on a porch and enjoy the afternoon. It is the kind of light that says, I am burning through my fuel at a pace that would make a billionaire's spending habits look conservative, and I have no intention of slowing down. You settle at a respectful distance, say a few light years, because getting any closer to a blue supergiant is the cosmic equivalent of standing next to a bonfire in a gasoline suit, and you watch. From here, the star is just a brilliant point, but in your mind's eye, you can see what is happening inside. The core is a furnace of nuclear fusion, and it has been working through the periodic table like a chef preparing a multi-course meal. For most of its life, perhaps 8 or 10 million years, it fused hydrogen into helium. That was the main course, the long stable phase called the main sequence, where the outward pressure of radiation balanced perfectly against the inward pull of gravity. A delicate equilibrium, a star in harmony with itself, but hydrogen runs out. It always does, in the cores of massive stars, and when it does, the core contracts under its own weight, heating up until helium nuclei begin fusing into carbon and oxygen. This phase is shorter, maybe 1 million years. Then helium runs out in the core and the process repeats. Carbon fuses into neon and magnesium. Neon fuses into oxygen and more magnesium. Oxygen fuses into silicon and sulfur. Each new fuel ignites at a higher temperature and burns for a shorter time. The carbon burning phase might last 1,000 years. Neon burning, perhaps a single year. Oxygen burning, a few months. And then silicon begins to fuse, and this final stage lasts roughly 1 day. 1 day. After millions of years of steady burning, the star's core sprints through its last fuel source in about 24 hours, producing iron. And here is where the story turns dark. Iron is the end of the line. Every fusion reaction before iron released energy, which is what kept the star alive, what kept that outward pressure pushing against gravity's relentless inward squeeze. But fusing iron does not release energy. It consumes it. Iron is the accounting ledger of stellar fusion, and when the core fills with it, the books no longer balance. There is a wonderful and slightly horrifying analogy that astrophysicists sometimes use. It is like a cartoon character running off a cliff, leg still spinning, and then looking down. For a brief moment, nothing happens, and then everything happens. The iron core, roughly the size of Earth but containing about 1.5 times the mass of our Sun, collapses. Not slowly, not gracefully. It collapses at roughly 1/4 of the speed of light. In less than a second, the core goes from a sphere thousands of kilometers across to a ball of neutrons about 20 kilometers in diameter. Let that sink in for a moment. A mass greater than the Sun, compressing from the size of a planet to the size of a city in under a second. The density becomes so extreme that protons and electrons are squeezed together to form neutrons, and the collapsing material overshoots its equilibrium, bounces off the incompressible neutron core and sends a shockwave roaring outward through the rest of the star. This is the supernova, and calling it an explosion does not do it justice. It is the most energetic event in the universe short of the Big Bang itself. For a few weeks, this single dying star will outshine its entire host galaxy. Billions of stars, all by itself. The shockwave rips through the outer layers of the star at tens of thousands of kilometers per second, flinging them into space in an expanding cloud of gas and heavy elements. All that carbon, oxygen, silicon, iron, and dozens of other elements forged in the star's core and in the supernova's own fury gets scattered across light years of space. These are the elements that will eventually become planets, oceans, atmospheres, and yes, people. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was cooked inside a star that died like this one. You are quite literally made of star stuff. Carl Sagan said it best, and astrophysicists have been happily repeating it ever since, because it has the rare quality of being both poetic and scientifically accurate. But you're not here for the poetry tonight. You're here for what is left behind. And what is left behind depends on the mass of the original star's core after the explosion. If the remnant core is below about 2 to 3 solar masses, a threshold known as the Tolman-Oppenheimer-Volkoff limit, which is a mouthful, but physicists love naming limits after themselves, then neutron degeneracy pressure can hold it up, and you get a neutron star. A bizarre city-sized object spinning at hundreds of revolutions per second, with a magnetic field trillions of times stronger than Earth's. Weird, but stable. However, if the core exceeds that limit, even the pressure of neutrons packed shoulder to shoulder cannot resist gravity. And then, there is nothing left to stop the collapse. No force in the known universe can intervene. The core falls inward past the point where light can escape, an event horizon forms, and a stellar black hole is born. Quiet, dark, and permanent. The universe's most elegant act of destruction, and you just witnessed it in the time it took you to take a few slow breaths. Scientists still argue whether there is a sharp mass boundary between stars that leave behind neutron stars and those that produce black holes, or whether the transition is messier, influenced by the star's spin, metallicity, and the dynamics of the explosion itself. Some models suggest a range of masses where either outcome is possible, a coin flip performed by physics under extreme conditions. There is also the tantalizing possibility that some supernova fail entirely. The shockwave stalls, falls back, and the whole star collapses into a black hole without any visible explosion. A star simply vanishing from the sky. Astronomers have actually observed candidate events for these so-called failed supernovae, stars that brightened briefly and then disappeared, leaving no visible remnant. Imagine looking up one night, and a star you've known your whole life is simply gone. The nebula around you is still glowing with the aftermath of the explosion you just witnessed, and somewhere in its heart, cloaked in silence, your first black hole is waiting. The glow of the supernova remnant is fading now, those brilliant filaments of expelled gas cooling from white hot to a sullen red, drifting outward in slow, ragged curtains. And at the centre of it all, where the star's core used to burn with the fury of 1 billion hydrogen bombs per second, there is nothing. Or rather, there appears to be nothing. No light, no glow, no remnant ember, just a small region of space that looks ever so slightly wrong, like a thumbprint smudge on a window, bending the starlight behind it in ways that make your eyes uneasy. That is your stellar black hole, and you're going to walk through its anatomy layer by layer, peeling it apart like the most terrifying cosmic onion you have ever encountered. Start from the outside and work your way in. The first thing you would notice, if you were approaching from a great distance with sufficiently sensitive instruments, is the way the black hole warps the light from background stars. This effect is called gravitational lensing, and it is one of the most visually stunning predictions of general relativity. Light from stars behind the black hole does not just disappear, it bends around the black hole's gravitational field, following the curvature of space-time the way water follows the curve of a drain. Stars that should be hidden behind the black hole appear displaced, smeared, or even duplicated into luminous arcs and rings. If you could see the full effect in real time, it would look like the universe behind the black hole was being viewed through a funhouse mirror designed by someone with a PhD in differential geometry and a flair for the dramatic. As you drift closer, you enter a region where the gravitational field begins to seriously affect the trajectories of particles and light. And here you encounter the photon sphere. This is a shell around the black hole. For a non-rotating stellar black hole, it sits at 1.5 times the radius of the event horizon, where gravity is so intense that photons, particles of light, can travel in circular orbits. Think about that for a moment. Light, the fastest thing in the universe, the thing that always travels in straight lines through flat space-time, is being bent into a circle. If you hovered at the photon sphere and looked straight ahead, you would theoretically see the back of your own head, because light leaving the back of your skull could orbit the black hole and return to your eyes. In practice, this orbit is unstable. The slightest perturbation sends the photon either spiraling inward past the event horizon or escaping outward into space. It is the cosmic equivalent of balancing a marble on the tip of a needle. Technically possible, practically not something you would bet your life on. There is a charmingly odd historical footnote here. When Carl Schwarzschild first solved Einstein's field equations for a spherical, non-rotating mass in 1916, barely a year after Einstein published General Relativity, he did so while serving on the Eastern Front of World War I. He was calculating the geometry of space-time around an idealized point mass in a trench between artillery barrages while suffering from a painful autoimmune disease that would kill him within months. The solution he produced, now called the Schwarzschild metric, describes the simplest possible black hole, and it contains within it the photon sphere, the event horizon, and the singularity. Schwarzschild himself did not fully appreciate what his solution implied. He thought the singularity was a mathematical curiosity, not a physical reality. Scientists still argue whether Schwarzschild would have embraced or resisted the modern interpretation of his own equations. But his work remains the foundation upon which all black hole physics is built, scribbled into existence in one of the least likely classrooms in history. Moving inward past the photon sphere, you reach the innermost stable circular orbit, often abbreviated as the ISCO. This is the closest distance at which matter can orbit the black hole in a stable, circular path without spiraling inward. For a Schwarzschild black hole, the simple, non-rotating kind, the ISCO sits at 3 times the radius of the event horizon. Inside this boundary, there are no stable orbits. Any matter that drifts below the ISCO is committed to falling inward. It might take a few spiraling loops, shedding energy as it goes, but the destination is sealed. The ISCO is critically important for understanding how black holes interact with the matter around them, because it effectively marks the inner edge of any accretion disk. That swirling, superheated platter of gas and dust that forms when material falls toward a black hole. Everything outside the ISCO can orbit. Everything inside is on a one-way trip. And then finally there it is, the event horizon itself. You're close enough now to see its effects directly. The sky around you has become deeply strange. Stars above you, in the direction away from the black hole, appear normal, perhaps slightly blue-shifted as light falls toward you with a little extra energy. But below you, toward the black hole, there is a growing circle of absolute blackness. Not the blackness of deep space, which is merely the absence of nearby stars. This is a different kind of dark. It is the dark of a region where space-time curves so completely inward that no information, no signal, no light can climb back out. It is a shadow with depth, with presence, with a gravitational voice so deep that it vibrates below the threshold of comprehension. The radius of this event horizon is determined by a beautifully simple formula. For a non-rotating black hole, the Schwarzschild radius equals 2 times the gravitational constant times the mass, divided by the speed of light squared. For a stellar black hole of about 10 solar masses, that works out to roughly 30 kilometers, you could drive across it in 20 minutes on a highway. The entire boundary between the knowable universe and the unknowable interior of a black hole, for an object containing 10 times the mass of our Sun, fits inside a mid-sized city. There is a strange intimacy to that scale. It is not incomprehensibly large. It is not subatomically small. It is human-sized enough to grasp, which somehow makes it more unsettling. Below the event horizon, all roads lead to the singularity. Every possible trajectory, every direction through space-time curves inward. Time and space effectively swap roles in a way that is mathematically precise but conceptually bewildering. Falling toward the singularity is no longer a matter of moving through space. It becomes a matter of moving through time. The singularity is not a place ahead of you. It is a moment in your future, as unavoidable as tomorrow. You cannot dodge it any more than you can dodge next Tuesday. You hover here for a moment, just outside the event horizon, feeling the geometry of the universe bending around you like warm glass. The layers are clear now: the lensing halo, the photon sphere, the ISCO, the event horizon, and somewhere deep inside, the singularity. A simple, terrifying architecture. And now you're curious about what would happen if you actually crossed that boundary. You're curious, and curiosity has a way of making terrible decisions feel reasonable. So you let yourself drift closer. Not fast, not with any dramatic plunge, just a gentle, almost lazy descent toward the event horizon, the way a leaf settles onto the surface of a still pond. Except this pond has no bottom, and the leaf is you, and the water is the fabric of space-time twisted into a funnel of infinite depth. But sure, gentle, lazy, relaxing. That is the energy we're going for tonight. The first thing to understand about falling into a stellar black hole is that it is not a peaceful experience. This is where the concept of spaghettification enters the conversation, and yes, that is the real scientific term. Astrophysicists, for all their mathematical rigour and intellectual seriousness, looked at the process by which a human body would be stretched into a thin strand of atoms by tidal forces and said, "You know what that looks like? Spaghetti." And then they published papers using that word, with footnotes and peer review. It is one of the most delightful examples of physicists refusing to take their own terminology seriously, and honestly it makes the whole field more endearing. Here is how it works. Tidal forces are the difference in gravitational pull between 2 points at different distances from a massive object. You experience tidal forces right now, sitting on Earth. The Moon's gravity pulls slightly harder on the side of the Earth facing it than on the far side, and this difference is what causes ocean tides. The effect is gentle because the Moon is far away and not terribly massive. But near a stellar black hole, the gradient of gravitational force becomes savage. If you were falling feet first toward the singularity, the gravity at your feet would be significantly stronger than the gravity at your head, because your feet are closer to the centre of mass. This difference pulls you apart lengthwise. At the same time, the gravitational field lines converge toward the centre, squeezing you from the sides. So you're being stretched vertically and compressed horizontally, simultaneously. Your body elongates into a thin filament, a strand, a noodle, spaghetti. Eventually, the tidal forces exceed the electromagnetic forces holding your molecules together, and you're pulled apart at the atomic level. Then those atoms are pulled apart. Then those subatomic particles are pulled apart. It is thorough. Now here is a detail that matters more than you might expect. The size of the black hole determines when spaghettification begins relative to the event horizon. For a stellar mass black hole, say 10 solar masses, the tidal forces become lethal well before you reach the event horizon. You would be torn apart while still in the observable universe, still technically in a region where light could escape. Your destruction would be visible to a distant observer, assuming they had a powerful enough telescope and a sufficiently morbid sense of curiosity. This is because the event horizon of a stellar black hole is relatively small. Remember, about 30 kilometers for 10 solar masses, and the tidal gradient is extremely steep at that scale. The smaller the black hole, the more ferocious the tidal forces at the horizon. For much larger black holes, supermassive ones with millions or billions of solar masses, the event horizon is so enormous that the tidal forces at its surface are actually quite gentle. You could cross the event horizon of a supermassive black hole and feel absolutely nothing unusual. No stretching, no squeezing, no dramatic moment of crossing. You would sail right through, possibly checking your watch and wondering when the scary part was supposed to start. The scary part, of course, comes later, as you fall deeper and the tidal gradient steepens. But at the moment of crossing, nothing. This is one of those counterintuitive facts about black holes that catches people off guard. The biggest ones are, in a sense, the most hospitable at their borders. We will visit those later. For now, you are dealing with the small, vicious kind. There is a famous thought experiment that physicists love to trot out when discussing this scenario. Imagine two observers, one falling into the black hole and one hovering at a safe distance, watching. From the falling observer's perspective, they cross the event horizon in finite time. They check their watch, and the crossing happens at a specific, measurable moment. Then they continue falling inward, experiencing increasingly intense tidal forces until spaghettification finishes the job. From their point of view, the whole thing takes a finite amount of time, though admittedly not a pleasant amount. But from the distant observer's perspective, something deeply strange happens. As the falling person approaches the event horizon, their image redshifts. The light coming from them stretches to longer and longer wavelengths, shifting from visible light into infrared, then microwave, then radio. They appear to slow down, moving more and more sluggishly, as if wading through invisible molasses. Time dilation near the horizon becomes so extreme that the distant observer never actually sees the falling person cross the event horizon. They see them approach it asymptotically, getting closer and closer but never quite arriving, their image dimming and reddening until it fades below the threshold of detectability. From the outside, the person appears to freeze at the boundary and slowly vanish like a photograph left in the sun. Scientists still argue about the deeper implications of this observer-dependent experience. Does the falling person really cross the horizon? Does the question even make sense if no external observer can ever confirm it? This touches on profound issues in the philosophy of physics, questions about the nature of reality, observation, and what it means for an event to happen if it can never be witnessed from the outside. Roger Penrose, the Nobel Prize-winning mathematician, contributed a beautiful piece of fringe-adjacent thinking to this puzzle. His work on conformal diagrams, those elegantly simplified maps of space-time called Penrose diagrams, showed that the interior of a black hole is, in a formal mathematical sense, a separate region of space-time. Not just hard to reach, not just hidden, structurally distinct. It is as if the black hole carves out a pocket universe inside our own, connected only by that one-way door at the event horizon. What happens inside that pocket is causally disconnected from the rest of the cosmos. It cannot influence us, and we cannot observe it. The universe keeps secrets, and this is the vault. You pull back now, retreating from the event horizon with a slight shiver that has nothing to do with temperature. Your imaginary body is intact, your atoms still politely bonded to one another, and you have a newfound appreciation for the pasta aisle at the grocery store. But the question of who first confirmed that these nightmarish objects actually exist in the real universe is nagging at you, and the answer involves a blue supergiant, an invisible companion, a torrent of X-rays, and one of the most famous scientific wagers of the 20th century. The year is 1964, and a pair of Geiger counters strapped to a sounding rocket are hurtling above the Earth's atmosphere on a brief suborbital flight. The instruments are pointed at a patch of sky in the constellation Cygnus, the Swan, and what they detect will eventually settle a debate that has been simmering in theoretical physics for decades. The source they find is extraordinarily bright in X-rays, far too bright to be any ordinary star, and it is flickering in a way that suggests the emitting region is tiny, perhaps only a few hundred kilometers across. It is catalogued with the unromantic name Cygnus X-1, meaning the first X-ray source discovered in Cygnus. At the time, nobody's quite sure what it is, but within a few years, as better instruments sharpen the picture, a story begins to emerge that reads like a cosmic detective novel. Cygnus X-1, it turns out, is not a single object. It is a binary system, two objects locked in a gravitational dance, orbiting their common centre of mass every 5.5 days. One of them is visible, a blue supergiant star called HDE 226868, roughly 40 times the mass of our Sun, blazing with that same fierce blue-white light you saw earlier from your ringside seat at the supernova. The other is invisible. It emits no light of its own, but its gravitational influence is unmistakable. By studying the wobble of the blue supergiant, the way it rocks back and forth as the invisible companion tugs on it, astronomers calculated that the unseen object has a mass of roughly 15 solar masses, and that single number changes everything. Remember the Tolman-Oppenheimer-Volkoff limit from a couple of sections ago? That threshold above which neutron degeneracy pressure cannot support a collapsed stellar core. It sits at roughly 2 to 3 solar masses. 15 solar masses obliterates that limit. Whatever the invisible companion is, it cannot be a neutron star. It cannot be a white dwarf. There is no known form of matter that could be that massive and that compact and remain stable against gravitational collapse. The only thing it can be, according to general relativity, is a black hole. The X-rays are the giveaway. Material is being stripped from the surface of the blue supergiant by the black hole's gravity, a steady stream of gas flowing across the gap between the two objects. As this gas spirals inward toward the event horizon, it forms an accretion disk, and friction within the disk heats the gas to millions of degrees. At those temperatures, the gas radiates furiously in the X-ray part of the spectrum. The flickering tells you the emitting region is small, because an object cannot vary its brightness coherently faster than light can travel across it. A region that flickers on timescales of milliseconds must be only a few hundred kilometers in size. Everything points to the same conclusion. Cygnus X-1 contains a stellar black hole, and the X-rays are its signature, the scream of matter being devoured. This is where the famous bet comes in. In 1974, Stephen Hawking and Kip Thorne made a wager about Cygnus X-1. Hawking bet that it was not a black hole. This might seem strange given that Hawking had spent much of his career studying black holes, and arguably understood them better than almost anyone alive. But Hawking later explained his reasoning with characteristic wit. He had invested so much of his intellectual life in black hole physics that he wanted an insurance policy. If black holes turned out not to exist, at least he would win the bet and get a subscription to Private Eye magazine, which was what he had wagered. Thorne, for his part, bet that Cygnus X-1 was indeed a black hole, wagering a subscription to Penthouse. The scientific community watched this friendly gamble with amusement, but the underlying question was serious. In 1990, as the evidence became overwhelming, Hawking conceded. He reportedly broke into Thorne's office while Thorne was away and signed the bet, acknowledging defeat. Thorne got his magazine subscription. Hawking got the satisfaction of knowing his life's work was grounded in reality, and physics got its first confirmed black hole. There is something wonderfully human about this story. Two of the greatest minds in theoretical physics, wrestling with one of the most profound discoveries in the history of science, and they settled it with magazine subscriptions and a bit of breaking and entering. It reminds you that science is not conducted by disembodied intellects floating in some abstract realm of pure thought. It is done by people, messy, funny, competitive, occasionally petty people who happen to be extraordinarily good at mathematics. Now, Cygnus X-1 was the first black hole to be widely accepted by the scientific community, but the path to that acceptance was not smooth. Scientists still argue about the exact moment when the evidence crossed the threshold from suggestive to conclusive. Some point to the mass determination in the early 1970s. Others insist the clincher came later, with more refined observations from X-ray satellites like Uhuru and Einstein. There was genuine resistance, not from cranks or contrarians, but from careful scientists who understood that extraordinary claims require extraordinary evidence, and the claim that an invisible object with no surface and no light was lurking in a binary star system was about as extraordinary as claims get. A quirky footnote to the Cygnus X-1 story involves the blue supergiant companion itself. HDE 226868 is losing mass at a ferocious rate, roughly 100,000th of a solar mass per year, stripped away by the black hole's gravitational appetite. In cosmic terms, this is a fire hose of material, and it means the system is evolving. The black hole is growing, the supergiant is shrinking. Eventually, perhaps in a few 100,000 years, the supergiant will exhaust its own fuel and collapse. Whether it produces a neutron star or a second black hole depends on how much mass it has left at that point. If a second black hole forms, you would have a binary black hole system, two black holes orbiting each other, spiraling slowly inward over millions of years, radiating gravitational waves, until they eventually merge in an event so cataclysmic that it shakes the fabric of space-time itself. But that is a story for a later section. For now, you simply note the possibility and file it away, the way you tuck a bookmark into a novel you're not ready to finish. The stars around you continue their slow procession, and you drift away from Cygnus X-1 with a quiet respect for the blue supergiant and its invisible partner, the first confirmed black hole, the one that turned theory into reality and magazine subscriptions into scientific legend. And now you are wondering, if that one was hiding in plain sight, feeding off a companion star, how many more are out there, drifting in the dark, feeding on nothing, visible to no one? The answer, it turns out, is a staggering number. Estimates vary, but most astrophysicists believe there are somewhere between 100 million and 1 billion stellar black holes in the Milky Way alone. Let that number settle into your sleepy brain for a moment. 100 million to a billion in one galaxy. And the overwhelming majority of them are doing absolutely nothing. They are not feeding. They are not glowing. They are not announcing themselves with dramatic X-ray emissions or gravitational theatrics. They're just drifting through the galaxy like dark, silent icebergs in an ocean of stars, and finding them is one of the most fiendishly difficult challenges in modern astronomy. Cygnus X-1 was easy, relatively speaking. It had a companion star to feed on, and that feeding produced X-rays, which are basically the black hole equivalent of leaving the kitchen light on. An X-ray binary is a black hole that wants to be found, or at least one that cannot help being conspicuous. But the vast majority of stellar black holes are solitary. They formed from the collapse of massive stars, received a gravitational kick from the asymmetry of the supernova explosion, and went sailing off into the interstellar void with no companion, no accretion disk, no X-ray glow. They are the loners of the galaxy, the quiet ones at the party who stand in the corner and say nothing, except in this case the corner is a random patch of empty space, and the party is the entire Milky Way. So how do you find an invisible object that emits no light? You look for its gravitational fingerprint, and this is where the story of Gaia BH1 begins. In 2022, astronomers using data from the European Space Agency's Gaia spacecraft announced the discovery of the closest known black hole to Earth, sitting roughly 1,600 light-years away in the constellation Ophiuchus. Gaia is not an X-ray telescope. It is an astrometry mission, which means it measures the precise positions and motions of stars with extraordinary accuracy. By tracking a sun-like star that appeared to be wobbling back and forth in a telltale pattern, astronomers deduced that it was orbiting an unseen companion with a mass of roughly 10 solar masses. Too massive for a neutron star, too dark for any kind of ordinary star. The only explanation that fit was a dormant black hole, one that was not actively feeding and therefore invisible in X-rays. The discovery was remarkable not just for what it found, but for what it implied. If a stellar black hole could be hiding just 1,600 light-years away, practically next door in galactic terms, then the galaxy must be teeming with them. Gaia BH1 was followed shortly by Gaia BH2, another dormant black hole discovered through the same astrometric wobble technique, this one about 3,700 light-years away with a companion star on a much wider orbit. And then came Gaia BH3, announced in 2024, a genuinely surprising find. A dormant black hole of roughly 33 solar masses, making it the most massive stellar black hole ever found in the Milky Way. It sits about 2,000 light-years from Earth, orbited by an ancient metal-poor star that formed in the early days of the galaxy. Scientists still argue about how a black hole that massive could have formed in our galaxy. Standard models of stellar evolution predict that the most massive stars in metal-rich environments like the Milky Way lose too much mass through stellar winds to produce a black hole of 33 solar masses. Gaia BH3's progenitor star must have been unusually metal-poor, allowing it to retain more of its mass before collapsing. It is a clue about the conditions of the early Milky Way, a fossil from a time when the galaxy was younger and chemically simpler. There is another technique for finding solitary black holes, and it is almost absurdly elegant. Gravitational microlensing occurs when a massive object passes between a distant background star and the observer. The gravity of the intervening object bends and focuses the light of the background star, causing it to brighten temporarily. The brightening follows a characteristic curve, smooth, symmetric, achromatic, that depends on the mass of the lensing object. If the lens is a black hole, the background star brightens and dims over a period of weeks or months, and the duration of the event tells you the mass. In 2022, two independent teams using data from the Hubble Space Telescope announced the detection of what appeared to be an isolated black hole, roughly 7 solar masses in size, identified through microlensing. The object, designated MOA 2011B LG191/OGLE 2011B LG0462, a name that only an astronomer could love, was spotted drifting through the galaxy about 5,000 light-years away, bending the light of a more distant star as it passed. The quirky thing about microlensing is that it is entirely passive. The black hole does not need to be doing anything. It does not need a companion. It does not need an accretion disk. It just needs to happen to pass in front of a background star from our point of view. The catch is that this alignment is rare and unpredictable. You cannot point a telescope at a specific black hole and wait for it to lend something. You have to monitor millions of stars simultaneously and hope that one of them brightens in the right way at the right time. It is astronomy by patience, and the surveys that perform this work, like Ogle and MOA, have been staring at crowded starfields in the galactic bulge for decades, cataloguing thousands of microlensing events, most caused by ordinary stars, a handful by objects that might be black holes. You drift through the Milky Way now with a new awareness. The stars around you are not alone. Woven among them, invisible and silent, are millions of black holes. Some are ancient, formed in the galaxy's earliest epochs when massive metal-poor stars burned through their brief lives and collapsed. Some are younger, born from the deaths of blue supergiants in spiral arms still rich with star-forming gas. A few have companion stars that betray their presence through subtle wobbles or brilliant X-ray emissions, but most are utterly alone, sailing through the dark, felt by nothing, seen by no one, detectable only when the geometry of chance briefly aligns them with a distant star's light. There is something almost meditative about that image. A galaxy full of invisible travellers, objects of immense gravity and profound strangeness, going about their silent business while the visible universe blazes and sparkles around them, entirely unaware. You let the thought carry you forward, deeper into the galaxy, toward a class of black holes that are rarer, stranger, and far more controversial than the stellar variety. Objects that sit in the gap between the small and the colossal, and whose very existence has been questioned for decades. The gap is maddening. On one side you have stellar black holes, objects ranging from about 3 to perhaps 100 solar masses, born from the deaths of massive stars, well understood, widely observed, and no longer controversial. On the other side, you have supermassive black holes, monsters of millions to billions of solar masses squatting at the centres of galaxies, equally well established, equally beyond dispute. But between those two categories, in the range of roughly 100 to 100,000 solar masses, there is a class of objects that has haunted astrophysics for decades. Intermediate mass black holes, the middleweights, the missing link. And for the longest time, the evidence for their existence was maddeningly thin. You would think that finding an object of, say, 10,000 solar masses would be straightforward. It is far more massive than a stellar black hole. It should have a stronger gravitational signature, a bigger accretion disk, a brighter X-ray output. But intermediate mass black holes occupy an awkward niche. They are not massive enough to anchor an entire galaxy the way supermassive black holes do, sitting conveniently at the gravitational centre of 100 billion stars where everyone can see them, and they are not produced by the ordinary death of a single star, so they do not turn up in the same systematic surveys that find stellar black holes in X-ray binaries. They are, in a sense, homeless. If they exist, they are wandering through galaxies or lurking in dense stellar environments without a fixed address, and the universe is extraordinarily good at hiding things that do not have a fixed address. The most promising places to look for intermediate mass black holes are globular clusters, those ancient dense spherical collections of hundreds of thousands to millions of stars that orbit galaxies like glittering satellites. Globular clusters are old, often 10 to 12 billion years, nearly as ancient as the universe itself. They're also incredibly crowded. In the core of a typical globular cluster, stars are packed so closely together that the night sky, if you were standing on a planet in there, would be a blazing wall of light, thousands of stars visible to the naked eye, so bright you might never experience true darkness. And in that dense, chaotic environment, gravitational interactions between stars are constant and violent. You find yourself drifting toward one of the most famous globular clusters in the southern sky, 47 Tucanae. It sits about 13,000 light-years from Earth, a dense jewel of roughly 1 million stars orbiting the Milky Way's halo. From a distance, it looks like a luminous cotton ball, soft and round, deceptively peaceful. But inside, the stellar dynamics are anything but peaceful. Stars in the core of 47 Tucanae are interacting gravitationally on timescales of thousands of years. Close encounters, binary disruptions, stellar collisions, and a relentless process called mass segregation, where the heaviest objects gradually sink toward the center while lighter stars are flung outward. Over billions of years, this process concentrates the most massive objects, stellar black holes, neutron stars, heavy white dwarfs, into a dense knot at the cluster's heart. The question is whether those stellar black holes, once concentrated in the core, can merge with each other. If a stellar black hole of, say, 20 solar masses encounters another of similar mass, and if they lose enough energy through gravitational interactions or gravitational wave emission to spiral together and merge, the result is a black hole of roughly 40 solar masses. That new, heavier black hole sinks even deeper into the core, encounters more black holes, merges again. 40 becomes 80, 80 becomes 150. Over billions of years, through repeated mergers, you could theoretically build up an intermediate mass black hole at the center of the cluster, one bite at a time. It is a slow, grinding process, the gravitational equivalent of rolling a snowball downhill, except the snowball is made of collapsed space-time, and the hill is a 10 billion year timescale. Observations of 47 Tucanae have been tantalizing but inconclusive. Radio and X-ray studies have placed upper limits on the mass of any central black hole, generally suggesting that if one exists, it is no more than a few thousand solar masses. Some analyses of stellar motions near the cluster's center hint at a concentration of dark mass that could be a single intermediate mass black hole, but the signal can also be explained by a swarm of stellar mass black holes and heavy white dwarfs clustered together without any single dominant object. This is the fundamental difficulty. When you're trying to detect a single object of, say, 2,000 solar masses sitting amid 1 million stars, the gravitational signal is subtle, and the noise from all those other objects makes it incredibly hard to isolate. Scientists still argue fiercely about whether 47 Tucanae harbours an intermediate mass black hole. Some teams say yes, pointing to subtle kinematic signatures in the velocities of stars near the centre. Others say no, arguing that the data can be explained without invoking a single massive object. The debate has been going back and forth for over 2 decades, and it shows no sign of being resolved without significantly better observations, perhaps from the next generation of extremely large telescopes, or from space-based gravitational wave detectors sensitive to the frequencies produced by intermediate mass mergers. There is a wonderfully quirky detail buried in the history of globular cluster research. In the early 2000s, a team of astronomers studying the globular cluster G1 in the Andromeda Galaxy claimed to have found evidence for an intermediate mass black hole of roughly 20,000 solar masses. The claim was based on the velocities of stars near G1's center, measured using the Hubble Space Telescope. It generated enormous excitement and enormous skepticism. Subsequent analyses using different models and different assumptions produced wildly different mass estimates, ranging from definitely an intermediate mass black hole to probably just a concentration of dark stellar remnants. G1 became a cautionary tale about the difficulties of this kind of measurement, a reminder that seeing what you want to see in noisy data is one of the oldest traps in science. You linger near 47 Tucanae for a moment, watching the stars in its core jostle and drift in their ancient gravitational ballet. Somewhere in there, maybe, a middle-way black hole is sitting quietly, growing imperceptibly with each passing eon. Or maybe there is nothing but a crowd of stellar remnants, dense and dark but individually unremarkable. The uncertainty is frustrating, but it is also part of what makes this corner of astrophysics so alive. And the next candidate on your tour is far less ambiguous, a source so bright and so strange that it earned a name suggesting it might be something beyond anything astronomers had seen before. The object is called HLX-1, which stands for Hyperluminous X-ray Source 1, and the name alone should tell you that whatever this thing is, it is not being subtle about it. You leave the quiet uncertainty of 47 Tucanae behind and travel roughly 290 million light-years to a galaxy catalogued as ESO 243-49, an edge-on-lenticular galaxy that looks, from our vantage point, like a luminous disk seen in profile, and there, offset from the galaxy's centre, not the nucleus where you would expect a supermassive black hole to reside, but off to one side, embedded in the galactic disk, is a point source of X-rays so powerful that it outshines every other X-ray source in the galaxy by a wide margin. When HLX-1 was first identified in 2009 by a team led by Sean Farrell at the University of Leicester, the X-ray luminosity was the thing that grabbed everyone's attention. It was too bright, far too bright. Ordinary stellar black holes in X-ray binaries produce luminosities up to a certain theoretical maximum, called the Eddington limit, which is the point at which the outward pressure of radiation balances the inward pull of gravity. For a stellar black hole of, say, 20 solar masses, the Eddington luminosity sets a ceiling on how brightly the accretion disk can shine. HLX-1 was blasting through that ceiling as if it did not exist. Its peak X-ray luminosity was roughly 100 times higher than the Eddington limit for a typical stellar black hole, which meant one of two things. Either the physics of accretion was behaving in some wildly unexpected way, or the black hole at the centre of HLX-1 was much, much more massive than any stellar black hole had a right to be. Follow-up observations across multiple wavelengths, X-ray, optical, ultraviolet and radio, painted an increasingly coherent picture. The X-ray emission varied over time, cycling between bright outbursts and quieter periods, in a pattern consistent with a black hole episodically devouring clumps of matter from a nearby source. The spectral characteristics of the emission matched models of accretion onto a black hole in the range of 20,000 to 100,000 solar masses, squarely in intermediate mass territory. HLX-1 became, almost overnight, the single strongest candidate for an intermediate mass black hole that the astronomical community had ever seen. But where did it come from? This is where the story gets genuinely fascinating. HLX-1 is not at the centre of ESO 243-49. It is offset, sitting in the outskirts of the galaxy's disk. That location is a critical clue. One leading hypothesis is that HLX-1 is the remnant nucleus of a dwarf galaxy that was captured and partially consumed by ESO 243-49. In this scenario, a small galaxy with its own central black hole, an intermediate mass one, wandered too close to the larger galaxy and was tidally stripped. The stars and gas of the dwarf galaxy were torn away and absorbed, but the dense central black hole survived, now orbiting within the body of its captor like a stone swallowed by a river. This process, called galactic cannibalism, is one of the primary ways galaxies grow over cosmic time, and the idea that it might leave behind orphaned intermediate mass black holes is both elegant and slightly melancholy. The black hole at the heart of HLX-1, if this hypothesis is correct, is a survivor, the last remnant of an entire galaxy that no longer exists. There is a competing hypothesis, though, and scientists still argue about which one is more plausible. Some researchers have proposed that HLX-1 formed not from a devoured dwarf galaxy, but from runaway stellar mergers in a massive young star cluster. In this scenario, a particularly dense cluster of stars experienced a cascade of collisions in its core, building up an increasingly massive star that eventually collapsed into an intermediate mass black hole. This mechanism has been modelled extensively in computer simulations, and while it can produce black holes in the right mass range, it requires very specific initial conditions: a cluster that is massive enough, dense enough, and young enough for the collisions to occur before the cluster disperses. Whether nature actually produces these conditions frequently enough to account for objects like HLX-1 is an open question. A quirky and somewhat underappreciated detail about HLX-1 is that its X-ray outbursts appear to be quasi-periodic. They recur on timescales of roughly a year, which has led some researchers to speculate that the black hole is orbiting through a stream of gas on an eccentric orbit, scooping up material each time it passes through the densest part of the stream. If true, this would be an extraordinary piece of cosmic clockwork, a black hole on a schedule, dining at regular intervals like a particularly disciplined predator. The periodicity is not perfectly regular though, which introduces uncertainty about whether the pattern is real or an artifact of incomplete observations. More data is needed, and the X-ray telescopes capable of providing it, Chandra, XMM Newton, and their eventual successors, continue to monitor HLX-1 with keen interest. The broader significance of HLX-1 extends well beyond a single object in a single galaxy. If intermediate mass black holes exist, and if they are the stripped nuclei of dwarf galaxies consumed by larger ones, then they should be relatively common. Every large galaxy has grown by devouring smaller ones. The Milky Way itself has consumed dozens of dwarf galaxies over its lifetime, and is currently in the process of digesting several more, including the Sagittarius dwarf elliptical galaxy, which is being tidally shredded as it orbits through our galaxy's halo. Each of those devoured dwarfs might have carried a central black hole, and those black holes might still be out there, wandering through the Milky Way's disk and halo, dormant and invisible, detectable only if they happen to encounter enough gas to produce a brief flare of X-ray emission. The image is striking. Not just one galaxy's worth of hidden black holes to worry about, but multiple populations, stellar black holes born from supernovae, and now potentially dozens of intermediate mass black holes inherited from devoured galaxies, all drifting silently through the same galactic space. You're floating through a cosmic minefield of invisible gravitational wells, and the only reason it does not keep you up at night is that space is so unfathomably vast that the odds of encountering one are essentially zero. Essentially, not exactly, but essentially, sleep well. The question of how these middleweights form in the first place, whether through mergers, through galactic cannibalism, through some other mechanism entirely, is still one of the most active areas of research in astrophysics, and the answer, when it comes, may reshape our understanding of how black holes grow across all mass scales. The formation question is the one that keeps theorists up at night, and not in the cozy, sleepy way that you are experiencing right now. It is more of a staring at the ceiling, scribbling equations on napkins, arguing with colleagues at conferences kind of insomnia. Because intermediate mass black holes sit in a mass range that is genuinely difficult to reach through any single, well-understood mechanism. Stellar evolution can produce black holes up to maybe 100 solar masses. Supermassive black holes start at 1 million solar masses and go up from there. The gap in between is not just observational, it is theoretical, and bridging it requires some creative astrophysical engineering. The first and most intuitive pathway is the one you glimpsed in the globular cluster: runaway mergers. Picture a dense stellar environment, a young massive cluster or the core of a globular cluster, where stars are packed so tightly that gravitational interactions are frequent and sometimes violent. In such an environment, the most massive stars tend to sink toward the center through dynamical friction, a process where gravitational encounters with lighter stars gradually drain the kinetic energy of the heavy stars and cause them to spiral inward. Once concentrated in the core, these massive stars can physically collide and merge with one another. A star of 50 solar masses collides with one of 40 solar masses, producing a bloated, unstable megastar of 90 solar masses. That megastar collides with another before it has time to lose significant mass through stellar winds. The process repeats, building up an increasingly absurd stellar object, hundreds, maybe thousands of solar masses, that eventually collapses under its own weight into an intermediate mass black hole. The problem with this scenario is timing. Massive stars live fast and die young, and stellar winds strip mass from them continuously. For the runaway merger process to work, the collisions have to happen faster than the stars can lose mass through winds, and faster than they can explode as supernovae. This puts severe constraints on the density and age of the host cluster. Simulations suggest it is possible, but only in the densest, most massive young clusters, and only during a narrow window early in the cluster's life. Whether the universe produces enough of these extreme environments to account for a significant population of intermediate mass black holes is something scientists still argue about with considerable passion and occasionally raised voices at symposia. The second pathway involves gravitational wave-driven mergers of stellar black holes, and this one got a spectacular boost from the LIGO and Virgo gravitational wave detectors. When two stellar black holes in a binary system spiral together and merge, they produce a single black hole with a mass roughly equal to the sum of the two progenitors, minus the energy radiated away as gravitational waves. A merger of 230 solar mass black holes might produce a black hole of about 57 solar masses, with the remaining 3 solar masses converted into gravitational wave energy. A staggering amount of energy, briefly outshining the entire observable universe in gravitational wave luminosity. Now, if that 57 solar mass black hole is sitting in a dense cluster, it can acquire a new companion through gravitational capture, spiral together with that companion, and merge again and again. Each generation of mergers builds up the mass step by step, potentially pushing into intermediate mass territory after several generations. LIGO actually detected a hint of this process in 2019. The event designated GW 1905-21 involved the merger of two black holes with masses of roughly 85 and 66 solar masses, producing a remnant of about 142 solar masses. That remnant sits right at the lower boundary of the intermediate mass range. It was the first direct evidence that black holes in this mass range can form through mergers, and it sent a ripple of excitement through the astrophysics community that was almost as dramatic as the gravitational waves themselves. The 85 solar mass component was particularly interesting because it falls within the so-called pair instability mass gap, a range of masses between about 65 and 120 solar masses where stellar evolution models predict that black holes should not form. Stars massive enough to produce cores in this range are expected to be completely destroyed by pair instability supernovae, leaving no remnant at all. The existence of an 85 solar mass black hole in GW 1905-21 suggests that it was itself the product of a previous merger, a second-generation black hole formed from the collision of two smaller predecessors. It is mergers all the way down, or rather, all the way up. The third pathway is perhaps the most exotic, and it takes you back to the earliest moments of the universe. In the first few 100 million years after the Big Bang, before the first generation of stars had finished forming, the universe was filled with vast clouds of primordial gas, hydrogen and helium, pristine and uncontaminated by heavier elements. Under certain conditions, these clouds could collapse directly into black holes without ever forming a star first. This process, called direct collapse, requires the gas cloud to avoid fragmenting into smaller clumps that would form ordinary stars. If the cloud is warm enough, kept heated by a nearby source of ultraviolet radiation for instance, it can collapse monolithically, funneling tens of thousands or even hundreds of thousands of solar masses worth of gas into a single object that forms a massive black hole almost immediately. These direct collapse black holes would be born in the intermediate mass range and could serve as seeds that later grow into the supermassive black holes we see at the centres of galaxies today. This is a thrilling idea because it solves two problems at once. It explains where intermediate mass black holes come from, and it provides a mechanism for seeding the supermassive black holes that somehow managed to grow to billions of solar masses within the first billion years of cosmic history, a timescale that is uncomfortably short if you start with only stellar mass seeds. A quirky feature of the direct collapse model is that these primordial black holes would have formed in the halos of the earliest proto-galaxies, small gravitational wells of dark matter that later merged and grew into the galaxies we see today. Some of those original halos might not have merged into larger structures. They might still be out there as small, faint dwarf galaxies, or even as dark matter halos with no visible stars at all, each potentially harbouring an intermediate mass black hole at its centre, like a pearl inside an invisible oyster. You let these three pathways, runaway stellar mergers, gravitational wave-driven hierarchical mergers, and direct collapse of primordial gas, orbit each other in your mind like competing theories at a conference. Each has strengths, each has weaknesses, and the truth, as it so often does in astrophysics, probably involves all three operating simultaneously in different environments and at different epochs. The universe rarely limits itself to a single mechanism when several will do. You've spent enough time in the middle of the mass spectrum. The middleweights are fascinating, elusive, and endlessly debatable, but something much larger is calling to you now. You can feel it, actually. Not hear it, not see it, but feel it. A deep, steady gravitational tug pulling you inward toward the centre of the galaxy, where the stars grow denser and the light takes on a golden hue from billions of old, sun-like stars packed into an increasingly tight swarm. You're heading toward the heart of the Milky Way, and what lives there makes every black hole you've visited so far look like a pebble next to a mountain. Sagittarius A star, that is its name, written as SGRA star in the shorthand astronomers prefer, with the asterisk pronounced star. It sits at the precise gravitational centre of our galaxy, roughly 26,000 light-years from Earth, hidden behind vast clouds of interstellar dust that block visible light so thoroughly that you cannot see it with an optical telescope no matter how powerful. Everything we know about SGRA star comes from observations in radio waves, infrared light, and X-rays, wavelengths that can penetrate the dust and reveal the extraordinary drama unfolding at the galactic core. The mass of Sagittarius A star is approximately 4 million times the mass of our Sun. 4 million solar masses, compressed into a region smaller than the orbit of Mercury. The event horizon, if you could see it, would be roughly 12 million kilometers across, large by human standards, but laughably small compared to the galaxy it anchors. The entire gravitational architecture of the Milky Way, 100 billion stars orbiting in a disk 100,000 light-years across, pivots around this one invisible point. It is the drain at the centre of a cosmic bathtub, except the bathtub is 100,000 light-years wide, and the drain, relatively speaking, is the size of a pinhead. The most direct evidence for Sagittarius A star's mass comes from decades of painstaking observations of stars orbiting near the galactic centre. Two teams, one led by Andrea Ghez at UCLA, the other by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics, spent years tracking the motions of individual stars in the crowded central region using adaptive optics on the world's largest telescopes. Adaptive optics is a technology that corrects for the blurring caused by Earth's atmosphere in real time, deforming the telescope's mirror hundreds of times per second to compensate for atmospheric turbulence. Without it, the stars near the galactic center would blur into an indistinguishable smear. With it, individual stars pop into focus, and their orbits can be tracked year by year. The star that proved most useful is designated S2, sometimes called S0-2, depending on which team's naming convention you prefer. S2 orbits Sgr A star on a highly elliptical path with a period of about 16 years. At its closest approach, it screams past the black hole at roughly 3% of the speed of light, passing within just 17 light hours of the event horizon. By tracking S2 through a complete orbit, both teams independently calculated the mass of the central object to extraordinary precision. The result, 4 million solar masses give or take, is now one of the most robust measurements in all of astrophysics. Gers and Genzel shared the 2020 Nobel Prize in Physics for this work, along with Roger Penrose, who was recognized for his theoretical proof that black hole formation is a robust prediction of general relativity. There is a delightful and somewhat rebellious tidbit buried in the S2 observations. As S2 swung through its closest approach to Sgr star in 2018, both teams detected a subtle but unmistakable gravitational redshift in the star's light, exactly the effect predicted by general relativity, where light climbing out of a deep gravitational well loses energy and shifts to redder wavelengths. This was the first time gravitational redshift had been measured for a star orbiting a supermassive black hole, and it served as yet another confirmation that Einstein's century-old theory holds up even in the most extreme gravitational environments in the galaxy. Some fringe theorists had hoped that observations near Sgr star might reveal deviations from general relativity, cracks in Einstein's framework that could point toward new physics. So far, Einstein keeps winning, which is either reassuring or slightly disappointing depending on how much you are hoping for a revolution. Scientists still argue about whether Sgr star is truly quiescent or merely dormant. Right now, it is remarkably quiet for a supermassive black hole. Its luminosity is roughly 100 million times lower than what it could produce if it were actively feeding at its Eddington limit. It is barely snacking, nibbling on the occasional wisp of gas that wanders too close, producing feeble X-ray flares that would be entirely unremarkable if they were not coming from a 4 million solar mass black hole. But there is evidence that Sgr star was not always this subdued. Observations of the Fermi bubbles, enormous lobes of gamma-ray emission extending above and below the galactic plane, suggest that Sagittarius A star experienced a period of vigorous feeding a few million years ago, producing powerful jets that inflated these bubbles like cosmic balloons. If you could rewind the clock just a few million years, the centre of the Milky Way might have looked very different. Brighter, more violent, perhaps even resembling the active galactic nuclei you see in distant galaxies. The idea that every large galaxy harbours a supermassive black hole at its centre is now one of the cornerstone principles of modern astrophysics. It was controversial when it was first proposed in the 1960s and 1970s, but decades of observations have made it almost axiomatic. The Milky Way has Sgr star. The Andromeda Galaxy has a supermassive black hole of roughly 140 million solar masses. Even small galaxies appear to host central black holes, though less massive ones. The relationship between a galaxy and its central black hole is intimate and reciprocal. The galaxy feeds the black hole, and the black hole, through its energetic outbursts, regulates the galaxy's growth. It is a cosmic partnership, sometimes nurturing, sometimes destructive, always fascinating. You're deep in the galactic core now, surrounded by the golden glow of ancient stars, and the invisible presence of Sagittarius A star fills the space around you like a bass note too low to hear, but heavy enough to feel in your bones. And somewhere out there, far beyond the Milky Way, a telescope the size of a planet has captured the shadow of a black hole even more massive in a galaxy 55 million light-years away. The image is everywhere. You've seen it even if you do not remember the context. A blurry, glowing, lopsided ring of orange and yellow light surrounding a dark central shadow, looking like a cosmic donut photographed through a fogged-up lens. It was released on April 10th, 2019, and it became one of the most widely shared scientific images in human history within hours. The object at its centre is the supermassive black hole in the galaxy Messier 87, designated M87 star, and the story of how that image was captured is almost as extraordinary as the black hole itself. M87 is a giant elliptical galaxy sitting near the centre of the Virgo cluster, roughly 55 million light-years from Earth. It is enormous, several times the mass of the Milky Way, and at its heart lies a black hole of approximately 6.5 billion solar masses. Not million, billion. That is over 1,000 times more massive than S-Gray star, and its event horizon is correspondingly gigantic, stretching roughly 38 billion kilometers across. If you placed it at the center of our solar system, the event horizon would extend well past the orbit of Pluto. It is a black hole on a scale that makes the word supermassive feel almost inadequate. Imaging this object required the Event Horizon Telescope, or EHT, and describing it as a telescope is both technically accurate and slightly misleading. The EHT is not a single instrument. It is a network of radio telescopes scattered across the globe, in Hawaii, Arizona, Spain, Chile, Mexico, the South Pole, and several other locations, all synchronized to observe the same target simultaneously. By combining the data from all these stations using a technique called very long baseline interferometry, the EHT effectively creates a virtual telescope with an aperture equal to the diameter of the Earth. This gives it the angular resolution needed to see details as small as the event horizon of M87 star from 55 million light-years away. To put that resolution in perspective, it is equivalent to standing in New York and reading the date on a coin in Los Angeles. Or, if you prefer a less American analogy, standing in London and reading a newspaper headline in Moscow. The observations themselves were conducted in April 2017, over 4 nights when weather conditions at all the participating sites were simultaneously good enough to collect useful data. This is harder than it sounds. Radio observations at the frequencies used by the EHT, around 230 GHz, are severely affected by water vapour in the atmosphere. A cloudy day at any one site could compromise the entire observation. The fact that all sites had clear skies simultaneously for multiple nights in a row was a stroke of luck that the team had been waiting years for. The data collected was staggering in volume. Each telescope recorded at a rate of 64 gigabits per second, filling banks of hard drives that eventually totaled roughly 5 petabytes, 5 million gigabytes of raw data. This was so much data that it could not be transmitted over the internet. The hard drives had to be physically shipped to 2 central processing facilities, one at MIT Haystack Observatory in Massachusetts, and one at the Max Planck Institute for Radio Astronomy in Bonn. The hard drives from the South Pole Telescope could not even be shipped until the austral winter ended and flights resumed, which meant the team had to wait months for the final dataset to arrive. There is something charmingly old-fashioned about the fact that the most technologically ambitious observation in the history of astronomy was bottlenecked by the Postal Service. Once all the data was assembled, the real work began. Converting the raw radio signals into an image required sophisticated algorithms that could fill in the gaps between the telescope stations, because even with a planet-sized array, the coverage is sparse, like trying to see your reflection in a mirror that is mostly missing. Multiple independent teams were tasked with processing the data using different algorithms without communicating with each other to ensure that the final image was robust and not an artifact of any single method. When all the teams independently produced essentially the same image, a bright ring of emission with a dark central shadow, the excitement was electric. Katie Booman, a computer scientist then at MIT who had developed one of the key imaging algorithms called CHIRP, became the public face of this achievement when a photograph of her reacting to the first image went viral. She was 29 years old, and she'd helped humanity see the unseeable. What you're actually seeing in that famous image is not the event horizon itself. You're seeing the hot glowing gas in the accretion disk in the region near the photon sphere, backlit and warped by the black hole's gravity into a ring. The dark central region is the black hole's shadow, the silhouette cast by the event horizon against the glowing background. The ring is brighter on one side than the other because of relativistic beaming. The gas orbiting the black hole at nearly the speed of light appears brighter when it's moving toward you and dimmer when it is moving away, a consequence of special relativity that makes the approaching side of the disk glow more intensely. Scientists still argue about some of the finer details of the M87 star image. The exact spin of the black hole, for instance, is still debated. The orientation of the accretion disk relative to our line of sight introduces uncertainties, and the role of the powerful relativistic jet that M87 star launches, a beam of plasma extending over 5,000 light-years from the galactic centre, in shaping the emission near the event horizon is not fully understood. Subsequent EHT observations have shown that the ring structure changes over time, with the bright spot moving around the ring as the turbulent accretion flow evolves. The black hole's shadow, however, remains fixed, a constant dark anchor in a sea of swirling light. In 2022, the EHT released a second landmark image, this time of Sagittarius A star, the Milky Way's own supermassive black hole. It showed a similar ring and shadow structure, though the image was harder to produce because Sagittarius A star, being 1,000 times less massive than M87 star, varies on much shorter timescales. The gas around Sagittarius A star changes noticeably in minutes, compared to days or weeks for M87 star, making the imaging process akin to photographing a toddler who will not sit still versus a sleepy grandparent in an armchair. Both images confirm the predictions of general relativity with remarkable precision. The shadows were the right size, the right shape, and in the right location. Einstein once again would have been quietly satisfied. The image of M87 star showed you the shadow, the silhouette, the dark outline of a monster backlit by its own dinner. But to truly understand what is happening around a supermassive black hole, you need to look at that dinner more closely. The accretion disk, the swirling, screaming, superheated platter of gas and plasma that forms when material falls toward a black hole and, rather than plunging straight in, gets caught in a spiraling descent that can last thousands of years. This is where the real violence happens, and paradoxically, it is this violence that makes black holes visible at all. Black holes, remember, emit no light of their own. Every photon you have ever seen attributed to a black hole actually came from the tortured material around it, and the accretion disk is the primary stage for that torture. You position yourself above an active galactic nucleus, not M87 specifically, but an idealized one, a supermassive black hole that is feeding vigorously. Below you, stretching outward from just beyond the innermost stable circular orbit, is the disk. It is not a solid thing, not a dinner plate or a vinyl record, though those analogies get thrown around a lot. It is a turbulent, seething flow of gas, mostly hydrogen and helium with traces of heavier elements, organised into a roughly flattened structure by the conservation of angular momentum. The gas wants to fall inward, gravity insists upon it, but it is spinning too fast to fall straight in. so it spirals, shedding angular momentum through friction and magnetic turbulence, gradually working its way inward over long timescales. The friction is the key, as parcels of gas at slightly different orbital radii rub against each other, or more accurately, as magnetic field lines tangled in the plasma create turbulent viscosity through a process called the magnetorotational instability. Kinetic energy is converted into thermal energy, heat, extraordinary, savage, inconceivable heat. The inner regions of an accretion disk around a supermassive black hole can reach temperatures of billions of degrees. At those temperatures, the gas does not merely glow. It radiates across the entire electromagnetic spectrum: radio, infrared, visible, ultraviolet, X-ray, and even gamma ray. The total energy output can be astonishing. A supermassive black hole feeding at a healthy rate can outshine its entire host galaxy, converting the gravitational potential energy of infalling matter into radiation, with an efficiency of about 10%. That may not sound impressive until you compare it to nuclear fusion, the process that powers stars, which converts mass to energy with an efficiency of roughly 0.7%. Accretion onto a black hole is over 10 times more efficient than the nuclear furnace of a star. It is the most efficient energy-generating process in the known universe, short of matter-antimatter annihilation. Above and below the disk, things get even more dramatic. In many active black hole systems, a pair of relativistic jets erupts from the polar regions, perpendicular to the disk, shooting narrow beams of plasma outward at speeds approaching 99% of the speed of light. These jets can extend for thousands, sometimes millions of light years, punching through the interstellar medium of their host galaxy and ploughing into intergalactic space, inflating vast lobes of radio-emitting plasma that dwarf the galaxy itself. M87's jet is one of the most famous, a luminous spike of plasma visible in optical telescopes, first photographed by Heber Curtis in 1918, long before anyone understood what it was. Curtis described it as a curious straight ray emanating from the galaxy's nucleus. He had no idea he was looking at the exhaust of a 6.5 billion solar mass black hole. The mechanism that produces these jets is one of the most actively studied problems in astrophysics, and scientists still argue about the details. The leading theory, developed by Roger Blandford and Roman Znayak in 1977, proposes that the jet is powered by the rotational energy of the black hole itself. A spinning black hole drags space-time around with it, an effect called frame dragging, and this rotating space-time, threaded by the magnetic field lines of the accretion disk, can extract energy from the black hole's spin and channel it into the jets. In essence, the black hole acts as a cosmic flywheel, and the magnetic field acts as the mechanism that taps that rotational energy and converts it into the kinetic energy of the jet plasma. The Blandford-Znayak process is elegant and mathematically well supported, but testing it observationally is extraordinarily difficult because the jet launching region is tiny, just a few times the size of the event horizon, and even the EHT barely resolves it. There is a quirky and somewhat mind-bending consequence of relativistic jets that is worth a brief detour. When a jet is pointed almost directly at Earth, the plasma moving toward us at nearly the speed of light creates an optical illusion called superluminal motion. Components of the jet appear to move across the sky faster than the speed of light. They're not actually exceeding the cosmic speed limit. It is a geometric projection effect, like how the dot of a laser pointer can sweep across a distant wall faster than light if you flick your wrist quickly enough. The dot is not a physical object, just a pattern, and no information is transmitted faster than light. Similarly, the apparent superluminal motion in jets is an illusion caused by the jet plasma nearly keeping up with its own emitted light. When this was first observed in the 1970s, It caused genuine confusion and a flurry of papers proposing exotic explanations before the correct geometric interpretation was widely accepted. You float above the accretion disk now, feeling the conceptual warmth of a billion-degree plasma, watching the jets lance outward into the void like searchlights at a cosmic premiere. The black hole below you is invisible, of course, but its presence is written in every photon, every particle trajectory, every warped magnetic field line around you. It is an engine of unimaginable power, converting the gravitational potential energy of infalling matter into light and motion, with an efficiency that makes every other energy source in the universe look quaint. And when this engine is running at full throttle, when the accretion rate is high and the luminosity is at its peak, the result is the most luminous steady phenomenon in the universe, visible across billions of light years, outshining galaxies by factors of hundreds. You've heard the name before, even if you did not know exactly what it meant. Quasar, and you're about to stare directly into one. The year is 1963, and a Dutch-American astronomer named Martin Schmidt is staring at a spectrum that makes no sense. He's working at the Palomar Observatory in California, studying an object catalogued as 3C273, the 273rd entry in the 3rd Cambridge catalogue of radio sources. Through the telescope, it looks like a star, a faint, unremarkable point of light in the constellation Virgo. But the radio emission coming from it is far too strong for any ordinary star, and when Schmidt spreads its light into a spectrum, the pattern of emission lines is unlike anything he has ever seen. The lines do not match any known element at any known temperature. For weeks the spectrum sits on his desk like an unsolved riddle, and then one day the answer hits him with the force of a revelation. The lines are hydrogen. Plain, ordinary hydrogen. But they are redshifted by an extraordinary amount, shifted toward longer wavelengths by a factor that indicates the object is receding from Earth at roughly 47,000 kilometers per second. Which means, according to Hubble's law relating recession velocity to distance, that 3C273 is not in our galaxy at all. It is over 2 billion light-years away. And that creates a problem, because if 3C273 is 2 billion light-years distant, then for it to appear as bright as it does in our sky, it must be producing an almost absurd amount of light. When Schmidt did the calculation, the result was staggering. 3C273 was shining with the luminosity of roughly 4 trillion suns. 4 trillion. That is about 100 times the total light output of the entire Milky Way, produced by a single source that looked like a star. Hence the name that quickly stuck, quasi-stellar radio source, or quasar. Schmidt's discovery opened a door that the astronomical community had not even realized was there. Over the following years and decades, thousands of quasars were identified, most of them at enormous cosmological distances, meaning their light had been travelling for billions of years. We were not seeing these objects as they are now. We were seeing them as they were billions of years ago in the youth of the universe, when galaxies were still forming and conditions were very different from today. Quasars, it turned out, were not a new type of star. They were the hyperactive nuclei of distant galaxies, powered by supermassive black holes feeding at or near their maximum rate. The accretion disk you floated above in the previous section, cranked up to full luminosity, is essentially what a quasar is, a supermassive black hole consuming matter so voraciously that the radiation from the accretion process outshines everything else in the galaxy by 100-fold. The realization that quasars were powered by black holes did not come immediately. Through the 1960s and into the 1970s, competing hypotheses abounded. Some astronomers proposed that quasars were chains of supernovae going off in rapid succession. Others suggested they were collisions between galaxies releasing enormous amounts of energy. A few even questioned whether the redshifts were cosmological at all, proposing that quasars might be nearby objects with intrinsic redshifts caused by unknown physics, a hypothesis championed most vocally by the astronomer Halton Arp, who pointed to apparent associations between quasars and nearby galaxies and argued that something was fundamentally wrong with the standard interpretation. Scientists still argue about Arp's legacy, whether he was a courageous contrarian who asked necessary questions or a stubborn outlier who refused to accept accumulating evidence. The mainstream consensus, however, settled firmly on the supermassive black hole model by the 1980s, as the energetics, variability, and spectral properties of quasars all pointed consistently toward accretion onto a compact, massive object. Here is a quirky fact that most people never encounter. The very first quasar ever observed was actually recorded on a photographic plate in 1896 at the Heidelberg Observatory in Germany, over 60 years before Schmidt figured out what quasars were. The object, later designated 3C48, appeared as an ordinary star in the image, and nobody gave it a second thought. It sat in astronomical archives, unremarked upon, for decades. It is a humbling reminder that seeing and understanding are not the same thing. The universe was showing us quasars for over half a century before we had the conceptual framework to recognize what we were looking at. Quasars have proven to be invaluable tools for cosmology, precisely because they are so luminous and so distant. They serve as cosmic lighthouses, illuminating the intervening space between them and us. As a quasar's light travels billions of light years to reach our telescopes, it passes through clouds of intergalactic gas, and each cloud absorbs a tiny sliver of the light at a specific wavelength corresponding to its own redshift. The result is a series of absorption lines in the quasar spectrum called the Lyman alpha forest, and by analysing this forest, astronomers can map the distribution of gas in the universe across billions of years of cosmic history. Quasars are not just spectacular objects. They are backlit maps of the universe's large-scale structure, and every new one discovered adds another data point to our understanding of how matter is distributed across the cosmos. The most distant quasars currently known are seen as they were less than 1 billion years after the Big Bang, and their existence poses a profound puzzle. The supermassive black holes powering these early quasars have masses of hundreds of millions to billions of solar masses. How did they get so massive so quickly? If you start with a stellar mass black hole of, say, 10 solar masses and feed it at the maximum possible rate, the Eddington limit, it takes roughly 1 billion years to grow to 1 billion solar masses. That is cutting it uncomfortably close, given that some of these quasars are seen at a time when the universe was only 700 or 800 million years old, and that assumes continuous, uninterrupted feeding at the maximum rate, which is physically unlikely. The black hole would need to start accreting almost immediately after the Big Bang, and never take a break. This is the supermassive black hole sea problem, and it is one of the motivations for the direct collapse and intermediate mass seed scenarios you explored a few sections ago. Something gave these early black holes a head start. Either they were born big, or they grew faster than standard models allow. Either way, the existence of quasars in the early universe is telling us something important about the conditions of the young cosmos that we do not yet fully understand. You drift away from the blinding core of the quasar, letting its light fade behind you, and you think about scale. 4 trillion suns, visible across billions of light years. And yet, as overwhelming as these objects are, there are black holes that make the engines of quasars look modest. Black holes so massive they strain the vocabulary of astrophysics and force us to coin new terms. You have entered the realm of the ultramassive. The word supermassive has always been a bit of a catch-all. It covers everything from the relatively modest SGRA star at 4 million solar masses to the engine of M87 star at 6.5 billion. That is a range of over 1,000, which would be like using the same word to describe both a house cat and a blue whale. Both are animals, sure, but the experience of encountering one versus the other is rather different. So in recent years, astronomers have begun informally using a new term for the truly colossal end of the spectrum, ultramassive. There is no universally agreed upon threshold, but the term is generally applied to black holes exceeding 10 billion solar masses, and the objects that qualify for this title are among the most extraordinary structures in the observable universe. Start with TON 618. This is a quasar, yes, one of those blinding accretion-powered beacons you just learned about, located roughly 10.5 billion light-years from Earth. The black hole at its centre has an estimated mass of 66 billion solar masses, 66 billion suns, compressed into a single object whose event horizon stretches roughly 400 billion kilometres across, larger than the entire Pluto orbit by a comfortable margin. If you could somehow see TON 618's event horizon superimposed on our solar system, it would swallow the Sun, all 8 planets, the Kuiper belt, and still have room left over for a modest existential crisis. The luminosity of the quasar powered by this black hole is roughly 140 trillion times that of our Sun, making it one of the most luminous objects ever observed. It shines with a cold, furious brilliance across a significant fraction of the observable universe, and the light reaching our telescopes today left TON 618 when the universe was only about 3 billion years old. You're looking at an ancient engine, a relic of a more violent epoch, still burning in the deep past. Then there is Cygnus A, discovered in 2022, by a team using gravitational modelling of stellar orbits in the central galaxy of the Phoenix cluster, a massive galaxy cluster roughly 5.5 billion light-years away. Cygnus A has an estimated mass of roughly 100 billion solar masses. 100 billion! That is the current record holder for the most massive black hole ever measured, though the measurement comes with substantial uncertainties, and scientists still argue about the precise figure. The galaxy hosting Cygnus A is itself a monster, a bloated central cluster galaxy that has grown fat over billions of years by cannibalizing smaller galaxies that fell into the cluster's gravitational well. Cygnus A likely grew alongside its host, fed by a steady stream of galactic mergers and cooling gas flows from the surrounding cluster medium. It is the apex predator of apex predators, an object so massive that trying to comprehend it in any intuitive way is a fundamentally doomed exercise. And then there is Holm 15 A star, the central black hole in the galaxy, Holm 15A, which sits at the core of the galaxy cluster Abell 85, about 700 million light-years from Earth. Its estimated mass is roughly 40 billion solar masses, making it one of the most massive black holes in the relatively nearby universe. What makes Holm 15 A star particularly interesting is not just its mass, but the peculiar structure of its host galaxy. Holm 15A has an unusually faint, diffuse core, a region at the galaxy's centre where the density of stars is much lower than expected. This is thought to be the scar left by binary black hole mergers. When two galaxies merge and their central black holes spiral together, the binary black hole system gravitationally ejects stars from the core, scooping out a deficit of stellar mass like a spoon hollowing out the centre of a melon. The bigger the black holes, the bigger the scoop. Holm 15A's depleted core is one of the largest ever observed, consistent with a history of multiple major mergers involving very massive black holes. The galaxy is essentially wearing the evidence of its violent past on its face, a gravitational scar that tells you how its central black hole got so enormous. The existence of ultramassive black holes raises a question that connects back to the quasar seed problem you encountered earlier, but with even sharper teeth. How do you grow a black hole to 100 billion solar masses? Even starting with a generous seed, say a direct collapse black hole of 100,000 solar masses formed in the early universe, you would need to sustain near-continuous accretion at or near the Eddington limit for billions of years, supplemented by repeated mergers with other supermassive black holes brought in by galactic cannibalism. The math works, but barely, and it requires a very specific set of circumstances. A galaxy that sits at the centre of a massive cluster, experiences frequent mergers, and has access to a large reservoir of cooling gas. Phoenix A and Holm 15A star both satisfy these conditions, which is encouraging, but the sample of known ultramassive black holes is still tiny, and whether current models can account for the full range of observed masses is a matter of ongoing and occasionally heated debate. There is a quirky theoretical limit worth mentioning here. In 2015, a paper by Andrew King at the University of Leicester proposed that there might be a maximum mass for a black hole, set not by any fundamental law of physics, but by the practical limits of the accretion process. King argued that once a black hole reaches roughly 50 billion solar masses, its accretion disk becomes so large and so gravitationally unstable that it fragments into stars rather than feeding the black hole. The disk essentially self-destructs, converting its gas into new stars before the gas can spiral inward. If this is correct, then black holes cannot grow much beyond about 50 billion solar masses through accretion alone. Growth beyond that limit would require direct mergers with other supermassive black holes, which are rare and slow. Phoenix A, at 100 billion solar masses, either challenges this limit or grew through an exceptional number of mergers. Scientists still argue about whether King's limit is a hard ceiling or merely a soft guideline, and the discovery of more ultramassive black holes in the coming years will help settle the question. You hover in the conceptual space between these titans, trying to hold 66 billion and 100 billion solar masses in your mind at the same time, and feeling the numbers slip away like sand through your fingers. These are objects that exist at the boundary of what language can describe and what intuition can grasp. And yet they are real. They are out there, right now, anchoring the largest galaxies in the largest clusters, silent and patient and incomprehensibly vast. The universe built them over billions of years, one meal at a time, and they will outlast nearly everything else in the cosmos. But the universe has an even stranger trick up its sleeve. Black holes that may have existed since the very beginning, born not from stars but from the fabric of space itself. You rewind. Not physically, you're not falling into a black hole backward, though that would be an interesting afternoon, but conceptually. You rewind all the way to the beginning, or as close to the beginning as physics will let you get, which is a tiny fraction of a second after the Big Bang. The universe is unimaginably hot, unimaginably dense, and expanding at a ferocious rate. There are no stars, there are no galaxies, there are not even atoms yet, not in the way you would recognize them. The cosmos is a seething soup of fundamental particles and radiation, and the rules governing its behavior are dictated by quantum mechanics and general relativity in a regime so extreme that both theories start to sweat. In this environment, something extraordinary might have happened. The early universe was not perfectly smooth. It was almost smooth, homogeneous to an astonishing degree, as the cosmic microwave background radiation later confirmed, but not perfectly so. Tiny quantum fluctuations, random variations in density from one microscopic patch to the next, were stretched to macroscopic scales by the rapid expansion of space during the epoch of cosmic inflation. Most of these fluctuations were small, mere ripples in the density field that would later grow into galaxies and galaxy clusters under the patient influence of gravity. But some fluctuations might have been large, anomalously large, and if a fluctuation was dense enough, if a particular patch of the early universe contained enough mass energy packed into a small enough volume, it could have collapsed under its own gravity right then and there, forming a black hole not from a dying star but from the raw stuff of the universe itself. These are primordial black holes. They were first proposed theoretically by Yakov Zeldovich and Igor Novikov in 1966, and the idea was significantly developed by Stephen Hawking and Bernard Carr in the 1970s. Unlike stellar or supermassive black holes, which form through astrophysical processes involving stars and gas, primordial black holes would be cosmological in origin, born from the initial conditions of the universe during its first fractions of a second, and their masses could, in principle, span an enormous range, from as light as a fraction of a gram to as heavy as thousands of solar masses, depending on the size and density of the fluctuation that produced them. The lightest primordial black holes would be genuinely tiny. A black hole with the mass of a mountain, say, 1 billion metric tons, would have an event horizon smaller than an atomic nucleus. You could hold it in your hand, if by hold it, you mean be instantly destroyed by its tidal forces and the burst of Hawking radiation emanating from its surface, which is admittedly a loose definition of holding. These substellar mass black holes are particularly interesting because they cannot be formed by any known astrophysical process. No star can collapse into a black hole lighter than about 2 or 3 solar masses. If you ever found a black hole with the mass of, say, the Moon, it would be almost incontrovertible evidence for primordial formation, because nothing in the modern universe can make one. The idea that primordial black holes might constitute some or all of the dark matter in the universe is one of the most tantalizing and hotly debated hypotheses in cosmology. Dark matter, as you may know, is the mysterious substance that makes up roughly 27% of the universe's total mass energy content. It does not emit, absorb, or reflect light. It interacts with ordinary matter only through gravity. Its existence is inferred from the rotation curves of galaxies, the dynamics of galaxy clusters, the pattern of the cosmic microwave background, and the large-scale structure of the universe. Decades of searches for dark matter particles, WIMPs, axions, sterile neutrinos, have come up empty. No detector has made a confirmed detection. No collider has produced a dark matter particle. The null results are piling up like unanswered letters, and some physicists have begun to wonder whether dark matter is not a particle at all, but rather a population of primordial black holes, invisible and gravitationally dominant, seeded in the first instance of cosmic history. The hypothesis is appealing because it requires no new physics beyond general relativity. Primordial black holes are made of ordinary space-time curvature. They do not need exotic particles or undiscovered forces. They just need the right initial conditions, density fluctuations of the right amplitude at the right time. However, the observational constraints on primordial black holes as dark matter are severe and span a dizzying range of techniques. Microlensing surveys have searched for the characteristic brightening of background stars caused by primordial black holes passing in front of them. Observations of the cosmic microwave background constrain how many primordial black holes could have formed without disrupting the smooth, nearly uniform radiation field. The orbital dynamics of wide binary star systems place limits on how many massive compact objects could be lurking in the galaxy without perturbing stellar orbits. Gravitational wave observations from LIGO and Virgo constrain the merger rate of primordial black holes in certain mass ranges. The result of all these constraints is a patchwork of exclusion regions that rule out primordial black holes as the entirety of dark matter for most mass ranges, but not all. There remains a window, roughly in the range of asteroid to sublunar masses, where primordial black holes have not been conclusively ruled out. They could still be hiding there, too small to lens background stars detectably, too light to merge at rates LIGO could observe, and too tiny to affect the cosmic microwave background significantly. It is a narrow window, and it might close as observational techniques improve, but for now, it remains open. Scientists still argue about how seriously to take this possibility. Some consider it a long shot, a hypothesis that survives only because we have not yet developed the tools to kill it. Others see it as a genuine contender, a solution to the dark matter problem that has been hiding in plain sight since the 1970s. A quirky detail about primordial black holes is that their formation might be linked to specific features of the inflationary epoch, the brief period of exponential expansion that is thought to have occurred within the first trillionth of a trillionth of a trillionth of a second after the Big Bang. Certain models of inflation predict a spike in the power spectrum of density fluctuations at specific scales, which could produce a burst of primordial black hole formation at a corresponding mass. If primordial black holes are ever detected, their mass distribution could serve as a fossil record of inflation itself, encoding information about the physics of the very early universe that is inaccessible by any other means. They would be archaeological artifacts of the first instant of creation, and studying them would be like reading the diary of the newborn cosmos. You have never confirmed one. Nobody has. Primordial black holes remain theoretical, a prediction of physics that has not yet been observationally verified. But the search continues, and the tools grow sharper with each passing year, and whether or not they turn out to exist, the idea itself illuminates something profound about the relationship between the very large and the very small, between cosmology and quantum mechanics, between the structure of the universe and the fluctuations that seeded it. Even in their hypothetical state, primordial black holes connect the first fraction of a second to the present day, and they remind you that the smallest seeds can grow into the strangest things. Speaking of small things growing strange, there is a man sitting in a wheelchair in Cambridge, England in 1974, about to detonate a conceptual bomb that will reshape everything physicists thought they knew about black holes. His name is Stephen Hawking, and you have already met him twice in this journey, once conceding a bet about Cygnus X-1, and once proposing primordial black holes with Bernard Carr. But this is the moment for which he will be most remembered, the insight that transformed black holes from purely gravitational objects into thermodynamic ones, from eternal prisons into slowly evaporating puddles. This is Hawking radiation, and it is one of the most beautiful, unsettling, and fiercely debated ideas in the history of theoretical physics. The setup requires a collision between two frameworks that do not normally speak to each other. General relativity describes gravity and the large-scale structure of space-time. Quantum mechanics describes the behavior of particles and fields at the smallest scales. For most of physics, you can safely use one or the other without worrying about the intersection. But at the event horizon of a black hole, particularly a small one, both frameworks become relevant simultaneously. And when Hawking carefully applied quantum field theory to the curved space-time near a black hole's horizon, the result was shocking. Black holes are not black. They glow. The mechanism, in simplified terms, works like this. Quantum field theory tells us that the vacuum of space is not truly empty. It is a fizzing, restless sea of virtual particle-antiparticle pairs constantly popping into existence and annihilating each other on timescales so short that they normally have no observable effect. This is not metaphor. It is a well-tested feature of quantum field theory, confirmed experimentally through phenomena like the Casimir effect and the Lamb shift. Now, imagine one of these virtual pairs appearing right at the edge of a black hole's event horizon. Normally, the particle and antiparticle would recombine and vanish. But if one of the pair falls across the horizon while the other escapes, the pair is permanently separated. The escaping particle becomes real. It carries energy away from the black hole and can be detected by a distant observer. The infalling partner, through the peculiarities of the energy accounting near the horizon, effectively carries negative energy into the black hole, reducing its mass by a tiny amount. The net result is that the black hole emits radiation and slowly shrinks. This is Hawking radiation, and the temperature of this radiation, the effective temperature of the black hole, is inversely proportional to its mass. A stellar mass black hole of 10 solar masses has a Hawking temperature of roughly 6 billionths of a Kelvin, which is absurdly cold, far below the current temperature of the cosmic microwave background radiation that fills the universe at about 2.7 Kelvin. This means that stellar mass black holes are currently absorbing more energy from the cosmic background than they emit through Hawking radiation. They are gaining mass, not losing it. They will not begin to evaporate until the universe has expanded and cooled enough for the background temperature to drop below their Hawking temperature, which will take an almost incomprehensible amount of time, trillions upon trillions of years. But for smaller black holes, the story is very different. Remember those hypothetical primordial black holes from the previous section? A primordial black hole with a mass of roughly 1 billion kilograms, about the mass of a small asteroid, would have a Hawking temperature of over 100 billion Kelvin. It would be radiating furiously, emitting a torrent of photons, neutrinos, and even heavier particles, burning through its mass at an accelerating rate. As it shrinks, its temperature rises, and as its temperature rises, it radiates even faster. The process runs away exponentially in the final moments. A primordial black hole of about 500 million metric tons formed in the early universe would be reaching the end of its life right about now, 13.8 billion years later. Its final moments would be spectacular. A burst of high-energy gamma rays as the last remnants of the black hole evaporate in a flash of quantum fury. Astronomers have actually searched for these gamma ray bursts, using satellites like Fermi, looking for the telltale signature of a primordial black hole reaching the end of its long, slow burn. So far, none have been found, which places limits on how many primordial black holes of that particular mass could exist. But the search continues, because finding even one would be a simultaneous confirmation of primordial black holes and Hawking radiation, two theoretical predictions verified in a single observation. It would be, without exaggeration, one of the greatest discoveries in the history of physics. Hawking's insight did more than predict a new form of radiation. It forged a deep and unexpected connection between black hole physics, thermodynamics, and quantum information theory. In the early 1970s, just before Hawking's breakthrough, Jacob Bekenstein had proposed that black holes carry entropy, a measure of disorder or hidden information, proportional to the area of their event horizons, not their volumes. This was a radical idea because in ordinary physics the entropy of an object scales with its volume. A box twice as large can hold twice as many possible configurations of particles, and therefore has more entropy. But Bekenstein argued that for black holes, all the information about what fell in is encoded on the two-dimensional surface of the event horizon, like a hologram. Hawking's radiation confirmed and extended Bekenstein's conjecture. The 4 laws of black hole mechanics, formulated by Hawking, Bardeen and Carter, turned out to be not merely analogous to the 4 laws of thermodynamics. They were the 4 laws of thermodynamics applied to black holes. Temperature is Hawking temperature, entropy is horizon area, energy is mass. The analogy was not an analogy at all. It was an identity. There is something almost spiritually satisfying about this convergence. 2 seemingly unrelated branches of physics, the science of heat engines and the science of curved space-time, turning out to be the same science viewed from different angles. It is the kind of unification that physicists dream about, and it hints at deeper truths about the nature of reality that we are still struggling to articulate. Hawking himself described the discovery as the thing he was most proud of in his career. which is saying something for a man whose career included singularity theorems, cosmological no-boundary proposals, and best-selling books that made black holes a household concept. You sit with this for a moment, letting the elegance of it wash over you. Black holes radiate, they have temperatures, they have entropy, they are born, they live, and eventually, given enough time, they die. They are not eternal after all. They are mortal, just on timescales that make the current age of the universe look like the blink of an eye. And their mortality raises a question so profound that it has consumed theoretical physics for half a century and shows no sign of being resolved. The question is deceptively simple to state. If a black hole evaporates completely through Hawking radiation, what happens to the information about everything that fell into it? This is the black hole information paradox, and it has been tormenting physicists since Hawking first articulated it in the mid-1970s. To understand why it is a paradox and not merely an unsolved problem, you need to appreciate a fundamental principle of quantum mechanics: unitarity. In quantum mechanics, information is never destroyed. The equations that govern the evolution of quantum states are reversible. If you know the complete quantum state of a system at any given time, you can, in principle, calculate both its future and its past. Information might get scrambled, shuffled, or encoded in extraordinarily complicated ways, but it is never lost. This is not a negotiable feature of quantum mechanics. It is built into the mathematical structure of the theory at the deepest level. Remove unitarity, and quantum mechanics collapses. Probabilities stop adding up to 1. The theory stops making sense. Now consider what happens when you throw a book into a black hole. The book crosses the event horizon and falls toward the singularity. The information contained in the book, every word, every page, every molecular configuration, is now inside the black hole. From the outside, the black hole's event horizon grows slightly larger. Its mass increases by the mass of the book, and according to Bekenstein's formula, its entropy increases by a corresponding amount. So far, so good. The information is hidden behind the horizon, but it is not destroyed. It is just inaccessible to outside observers, locked away in the black hole's interior. But then the black hole evaporates. Over immense stretches of time, Hawking radiation carries away the black hole's mass, bit by bit, until nothing remains. And here is the crux of the problem. Hawking's original calculation showed that the radiation emitted by a black hole is exactly thermal. It is random. It carries no information about what fell into the black hole, any more than the heat radiating from a furnace tells you what was burned inside it. A black hole formed from the collapse of a star, and a black hole formed from the collapse of an equivalent mass of old textbooks would emit identical Hawking radiation. By the time the black hole is completely evaporated, all the information about the book and the star and everything else that ever fell in appears to be gone. Not hidden, not scrambled, gone, destroyed, which violates unitarity, which breaks quantum mechanics, which is, to put it mildly, a problem. Hawking himself initially believed that information was genuinely destroyed in black holes, and that quantum mechanics would need to be modified to account for this. He made this argument explicitly and forcefully, and it put him in direct conflict with much of the quantum physics community, who were unwilling to give up unitarity under any circumstances. The disagreement crystallized into one of the most famous intellectual battles in modern physics, with Hawking and Kip Thorne on one side arguing that information is lost, and John Preskill on the other arguing that it is not. In 1997, they formalized the dispute as a bet, another one, with Preskill wagering that information is preserved and Hawking and Thorne wagering that it is destroyed. The stakes were an encyclopedia of the winner's choice, on the grounds that information about information should be rewarded with more information. In 2004, Hawking conceded, he had come to believe, based on developments in string theory and the holographic principle, that information is indeed preserved and encoded in the Hawking radiation in a subtle, highly scrambled form. He gave Preskill a copy of Total Baseball, the ultimate baseball encyclopedia, which was either a deeply thoughtful choice or a characteristically dry joke. Thorne, notably, did not concede, and has maintained a more agnostic position. The concession did not settle the debate so much as shift its focus. If information is preserved, how? Through what mechanism does the Hawking radiation, which appears thermal and featureless in Hawking's original calculation, manage to carry away the precise quantum information about everything the black hole consumed? This is where the firewall debate enters the picture, and it is one of the strangest arguments in the history of physics. In 2012, 4 physicists, Ahmed Almeri, Donald Marolf, Joseph Polchinski, and James Sully, collectively known as AMPS, published a paper arguing that 3 widely accepted principles of physics cannot all be true simultaneously near a black hole. The 3 principles are: information is preserved in Hawking radiation, the event horizon is a smooth region where nothing dramatic happens to an infalling observer, and the laws of quantum field theory hold in the vicinity of the horizon. AMPS showed that these 3 principles are mutually contradictory. At least one must be wrong, and if you give up the smoothness of the horizon, the result is a firewall, a curtain of ultra-high energy radiation at the event horizon that incinerates anything crossing it. Forget spaghettification. Forget the gentle crossing of a supermassive black hole's horizon that we discussed earlier. In the firewall scenario, the event horizon is lethal, a wall of Planck temperature fire that destroys you and everything about you the instant you touch it. The firewall proposal sent shockwaves through theoretical physics. It seemed to violate the equivalence principle, the foundational insight of general relativity that says a freely falling observer should not experience anything special at the horizon. Dozens of counter-proposals emerged almost immediately. Leonard Susskind and Juan Maldacena proposed the ER equals EPR conjecture, suggesting that quantum entanglement between Hawking radiation particles and their partners inside the black hole is physically realized as microscopic wormholes connecting the interior to the exterior. This would allow information to escape without a firewall, preserving both smoothness and unitarity. It is a beautiful idea, but it remains unproven. Others have proposed that the interior of the black hole is reconstructed from the Hawking radiation through quantum error correction codes, treating the horizon as a kind of holographic encoding surface. Scientists still argue passionately about which, if any, of these proposals is correct. The information paradox remains officially unsolved, a gaping wound in our understanding of the universe that refuses to heal. You let the paradox sit in your mind without trying to resolve it, the way you might hold a question in the dark without demanding an answer. Some questions are better as companions than as puzzles, and far away, across the void, 2 black holes are spiraling toward each other in a dance that will shake the very fabric of space-time and open an entirely new way of listening to the universe. The signal lasted less than a second, a faint rising chirp sweeping upward in frequency like a bird call played at 1,000 times normal speed, starting low and ending in a sharp burst before falling silent. It arrived at the LIGO detector in Livingston, Louisiana, on September 14th, 2015 at 5:51 in the morning local time, and 7 milliseconds later, it arrived at the twin detector in Hanford, Washington, 2,700 kilometers away. The 7-millisecond delay told the scientists the direction the signal came from. The shape of the chirp told them everything else. 2 black holes, one 36 solar masses and the other 29, had been spiraling toward each other for millions of years, orbiting faster and faster, closer and closer, until in the final fraction of a second they collided and merged into a single black hole of 62 solar masses. the missing 3 solar masses, 3 times the mass of our Sun, had been converted into gravitational wave energy and radiated outward in a ripple of space-time that travelled for 1.3 billion years before gently stretching and squeezing the 4-kilometre arms of the LIGO detectors by a distance smaller than 1/10,000th the diameter of a proton. That is the measurement, 1/10,000th the diameter of a proton. If that does not make you pause and marvel at the sheer audacity of experimental physics, nothing will. LIGO, the Laser Interferometer, Gravitational Wave Observatory, works by splitting a laser beam, sending each half down a 4-kilometre vacuum tube at right angles, bouncing them off mirrors and recombining them. When a gravitational wave passes through, it stretches space along one arm and compresses it along the other, causing the laser beams to travel slightly different distances. This produces an interference pattern that shifts by a measurable amount. The precision required is almost absurd. The mirrors must be isolated from every conceivable source of vibration, traffic, ocean waves, even the quantum fluctuations of the laser light itself. The engineering challenges were so severe that the project nearly died multiple times during its decades-long development. Kip Thorne and Rainer Weiss, 2 of the founders, fought for funding through years of skepticism from colleagues who thought the measurement was simply impossible. When the detection finally came, it was so clean, so textbook perfect, that the team spent months verifying it was not a test signal accidentally injected into the system. It was not. It was real. The event, designated GW150914, was the first direct detection of gravitational waves and the first direct observation of a binary black hole merger, and it earned Thorne, Weiss and Barry Barish the 2017 Nobel Prize in Physics. There is a wonderfully human detail buried in the timeline of this discovery. The detection happened during what LIGO engineers call an engineering run, a period of testing and calibration before the official observing run was scheduled to begin. The universe, it seems, did not care about the schedule. It sent its signal early, like a guest arriving at the party before the hostess finished setting up the chairs. Several team members later admitted that when they first saw the signal in the data, their initial reaction was not excitement but suspicion. Surely this was a blind injection, a fake signal secretly added to the data stream as a test of the analysis pipeline. The blind injection system had been used in previous runs, and the team had been fooled before. It took weeks of careful investigation to confirm that no injection had been made. The universe really had delivered a gravitational wave, perfectly timed and impossibly clear, as if it wanted to make absolutely sure humanity got the message. Since GW150914, the LIGO Virgo Cagra network has detected dozens of binary black hole mergers, along with binary neutron star mergers and neutron star black hole mergers. Each detection adds to a growing catalogue of black hole masses, spins and merger rates that is reshaping our understanding of stellar evolution and black hole formation. Remember GW190521, the event from a few sections ago that produced a 142 solar mass remnant in the intermediate mass range. That came from this catalogue. Every new observing run, with upgraded sensitivity and additional detectors, pushes the frontier further. The upcoming LISA mission, the Laser Interferometer Space Antenna, a trio of spacecraft separated by 2.5 million kilometres, forming a giant triangle in orbit around the Sun, will extend gravitational wave detection to much lower frequencies, opening a window onto the mergers of supermassive black holes, the inspiral of compact objects into massive black holes, and potentially the gravitational hum of primordial black holes or cosmic strings from the early universe. The chirp of a binary black hole merger encodes an extraordinary amount of information. The frequency evolution tells you the masses. The amplitude tells you the distance. The The spin and orientation of the black holes leave imprints on the waveform's shape. And the final ring down, the brief oscillation of the newly formed black hole as it settles into a stable configuration, tells you the mass and spin of the remnant. It is like listening to a bell being struck and deducing the size, shape, and composition of the bell from the sound alone. Gravitational wave astronomy is, in a very real sense, the art of listening to the universe. For 4 centuries, astronomy relied on light. Now it has ears. Scientists still argue about some of the implications of the growing gravitational wave catalogue. The mass distribution of merging black holes does not perfectly match predictions from stellar evolution models. There are more high-mass mergers than expected, and the spins of the merging black holes are often misaligned with their orbital angular momentum, which hints at dynamical formation in dense stellar environments, rather than isolated binary evolution. A quirky finding from the catalogue is that some merger remnants receive a gravitational recoil kick, an asymmetric emission of gravitational waves during the merger that propels the remnant black hole at speeds of up to several thousand kilometers per second. In some cases, this kick is fast enough to eject the black hole from its host galaxy entirely, sending it sailing into intergalactic space as a rogue black hole. The image is magnificent and slightly haunting, a freshly forged black hole, born from the most violent collision in the cosmos, booted out of its home and condemned to drift alone through the void forever. Multi-messenger astronomy takes this further. When LIGO detected the merger of 2 neutron stars in 2017, the event GW170817, the gravitational wave signal was accompanied by a burst of gamma rays detected by the Fermi satellite just 1.7 seconds later, followed by optical, infrared, ultraviolet, radio, and X-ray emissions observed by dozens of telescopes around the world. It was the first time a single astrophysical event was observed in both gravitational waves and electromagnetic radiation, and it confirmed that neutron star mergers are the source of short gamma-ray bursts and the cosmic forges where heavy elements like gold and platinum are created. Neutron star black hole mergers, also detected in the gravitational wave catalogue, bridge the gap between these 2 types of events and promise even richer multi-messenger observations as detector sensitivity improves. You listen, in your imagination, to the fading chirp of colliding black holes, a sound translated from gravitational waves into audio frequencies for human ears. It is a strange, alien song, a rising whoop that ends in a thud, and it carries within it the story of 2 objects that spent millions of years falling toward each other, moving imperceptibly at first, then faster, then impossibly fast, until the final plunge merged them into something new. And now you look ahead, past the mergers, past the quasars, past the ultramassive titans, to the farthest future the universe has to offer, where black holes are the last things left. The universe is patient. You have learned that by now, drifting through its dark corridors for the better part of this journey, watching stars ignite and die, watching black holes form and feed and merge. But you have not yet seen what happens when patience itself runs out, or rather, when patience is the only thing left. Fast forward, not a few billion years, not even a trillion. Go further. Let the numbers become meaningless. Let the zeros pile up like snow on a windowsill and arrive at an epoch so distant that the word future barely applies. This is the black hole era, and it is the longest chapter in the life of the universe, a chapter that will dwarf everything that came before it, the way an ocean dwarfs a puddle. The current age of the universe is about 13.8 billion years. The stelliferous era, the age of stars, the epoch we live in now, when hydrogen fuses and galaxies shine, will last perhaps another 100 trillion years, give or take. 100 trillion sounds like a lot, and it is, but it is a rounding error compared to what follows. after the last red dwarf sputters out, after the final dim ember of stellar fusion goes cold, the universe enters a long, dark autumn. White dwarfs cool into black dwarfs. Neutron stars spin down and fade. The galaxies, now dark and lifeless, gradually dissolve as gravitational encounters eject stars from their orbits one by one over timescales of quadrillions of years. Eventually, all that remains in any given region of space is a scattering of dead stellar remnants, a thin haze of particles, and black holes. And the black holes endure. They are the last macroscopic objects in the universe, sitting in the void like monuments in an abandoned city. Stellar black holes, intermediate mass black holes, supermassive and ultramassive black holes at the centres of long-dead galaxy remnants. They do not shine. They do not feed. There is nothing left to eat, or so little that accretion is negligible. They simply exist, holding their mass in the curved geometry of space-time waiting. But even they are not eternal. Hawking radiation, that whisper-thin quantum glow, is still operating, and now, with the cosmic microwave background cooled to effectively zero and no infalling radiation to replenish them, the black holes are finally losing more energy than they gain. They are evaporating. The timescale for this evaporation is staggering. A stellar black hole of 10 solar masses will take roughly 10 to the 67th power years to evaporate. That is a 1 followed by 67 zeros. Written out, it would fill a line of text longer than this entire script. A supermassive black hole of 1 billion solar masses will take approximately 10 to the 97th power years. And the ultramassive titans, the 100 billion solar mass monsters like Cygnus A, will persist for perhaps 10 to the 100th power years. A Google years, give or take. These numbers are so large that they defeat not just intuition but language itself. There is no analogy, no metaphor, no comparison that can make them feel real. They exist only as mathematical statements, cold and clean and absolute. During this impossibly long twilight, the black holes slowly shrink. Their Hawking temperatures rise imperceptibly as their masses decrease. A black hole that spent most of its life colder than the cosmic microwave background gradually warms, degree by infinitesimal degree, over timescales that make the current age of the universe look like the flash of a camera. Near the very end, the process accelerates. As the black hole shrinks to the mass of a mountain, its temperature soars to billions of degrees. It begins radiating visible light, then X-rays, then gamma rays. The final moments are explosive. A burst of high-energy particles and radiation as the last remnants of the black hole's mass are converted into energy. And then it is gone. Not collapsed, not hidden. Gone. The space-time curvature smooths out. The event horizon vanishes. Where once there was a black hole, there is nothing but a fading glow of radiation dispersing into the ever-expanding void. Scientists still argue about what happens in the very last instant of evaporation. Does the black hole vanish completely, or does it leave behind a tiny remnant, a Planck mass relic, stabilized by quantum gravitational effects at the smallest possible scale? If remnants are left behind, they might carry the information that fell into the black hole over its lifetime, resolving the information paradox in a quiet, anticlimactic way. If nothing remains, the information problem reasserts itself with full force. The final fate of an evaporating black hole is intimately tied to the deepest unsolved questions in physics, and until we have a working theory of quantum gravity, the answer will remain out of reach. One by one, across spans of time that no conscious being will ever witness, the black holes wink out. Stellar black holes go first, being the lightest, then the intermediate mass ones, then the supermassive. And finally, after a Google years or more, the last ultramassive black hole in the observable universe emits its final photon and disappears. The black hole era ends. What follows is the dark era, a universe of diffuse photons, neutrinos, electrons and positrons, drifting ever farther apart in an ever-expanding space, approaching but never quite reaching thermal equilibrium. Nothing happens, nothing will happen. The universe is not dead exactly, but it is as close to dead as physics allows. A vast, cold, empty expanse with no structure, no complexity, no change. Just entropy, maximized and absolute, stretching in every direction without end. And yet, even here, physicists find room for speculation. Could quantum fluctuations in this empty void occasionally produce, over unimaginably long timescales, a brief flicker of order? A Boltzmann brain, a momentary conscious observer assembled by pure chance from random particle interactions. Could an entire new universe nucleate from a quantum tunneling event in the vacuum, sparking a new Big Bang in some disconnected bubble of space-time? These ideas are speculative to the point of being unfalsifiable, but they remind you that physics never truly runs out of questions, even when it runs out of stars. You have travelled far enough now. You've visited every type of black hole the universe has to offer, stellar and intermediate, supermassive and ultramassive, primordial and theoretical. You have watched them born from the ashes of dying stars, grown from the seeds of the early cosmos, fed by rivers of superheated gas, merged in collisions that shook the fabric of space-time. You have peeled apart their anatomy, felt the tug of their gravity, and stared into the paradoxes they leave behind. And now, at the end of all things, you have watched them evaporate into the void, the last structures in a universe winding down to silence. So let your breathing slow. Let the images soften and blur, the way stars blur when you look at them through half-closed eyes. The black holes are fading now, one by one, like candles being gently blown out in a long, dark hallway. There is nothing to fear in that darkness. It is quiet. It is still. It is the kind of darkness that holds you rather than hides from you, the kind that wraps around your shoulders like a blanket and tells you that the day is done, that the questions can wait, that the universe, for all its violence and mystery and impossible scale, is also a place of deep, abiding calm. The last photon drifts, the last ripple smooths, and you, warm and safe and wonderfully small, let your thoughts dissolve into the soft hum of whatever room you're lying in, whatever night is pressing gently against your window. The cosmos will keep its secrets a little longer. You do not need to solve them tonight, just rest, just breathe, just sleep.